Or like way back there. Like those are the.
Can you hear me now?
So
Hello.
Are we? Is it going?
Yeah.
Are we still doing warm up stuff?
Okay. So the microphone is going to be over here.
Just be aware of that when you guys are talking.
Yeah.
Wait, what are we being aware of?
There's a hot mic.
Okay.
And it's there.
And it's
so
here.
When you guys are talking, make sure you're talking to that computer.
Okay.
Okay.
All right. Can't talk to you. I have to talk to this computer.
Have fun.
Wait, I've been told.
I'll be back.
It should pick you up if you're over there.
It will?
Yeah.
Oh, okay. So do you have? Oh, so you got the airdrop stuff and you got the slides?
Yeah, I'm set up. We'll
Okay.
start in 2 minutes.
Okay, we're starting in 2 minutes. So, so here, let me do this. So I'm Brad Miller, and I work over at WPI and do like future robotics class, and I kind of help with and try and organize a lot of the software releases that you guys use, the WPILib software that you use. And in particular, what we do is deal with C++ and Java, and then the guys over at National Instruments do the LabVIEW version of it. So that's kind of how it works. And so I've been doing this like for a long time. I started like around 2000. In 2001, I went to the championship when it was at Epcot Center, and then got hooked. And then haven't been able to get out since. And I've been trying, but it doesn't work. And so I've been doing this stuff since then. And also kind of we have P190, which is over WPI, so I'll do a little bit over there. But most of the time is doing this stuff, doing the software you guys have. And so and this is Austin Shellett.
Hello.
And he's a sophomore in robotics engineering and computer science. And he's doing a double major. And he's been also working on WPILib stuff for the last couple of years. And in particular, the thing which he is most proud of and doesn't stop talking about is this program called Outline Viewer, which lets you look at all the data which is inside of network tables, you know, the network stuff, which we'll talk more about a little bit later. But it's this stuff that lets you transfer data between like the RoboRio and your laptop, or RoboRio and a Raspberry Pi, or like whatever you have on the network. And,
you may also see me around at events.
Yeah, he also hangs out at events and helps. He's like an FTAA, so he's on the field all the time. So if your robot doesn't work or something, or stops in the middle of a match, then he'll be there to help you figure out what happened. So so that's who we are. Now, actually, there's a mob of people that are working on this stuff. So WPILib turned into an open source project about 2 or 3 years ago, or 3 years ago, I guess. And so all the source code and everything is all posted on this website called GitHub. You guys know what that is? We'll talk more about this. But everything is posted on GitHub, and so you can see the progress. You can see exactly what we're doing. And as we change software, change libraries, change the other programs, or anything like that, the stuff just gets pushed down to GitHub. So you see it as soon as we see it. It's like exactly. So you could kind of play with the stuff a little bit early. Although unfortunately, what happens is that when National Instruments flips to a new version of LabVIEW, they create a new image that goes into the RoboRio, which is the firmware for the RoboRio, and then what happens is that you and then what you need is a new image. So the beta teams get new images, but we don't release the new images to like everybody. So you can't really try the software once we get to the point where we've ported to the new image, and we're kind of there now because we're in the middle of beta. But you can look at it and you can see what there is. And some of the other programs like the dashboards and the outline viewer and stuff like that you can get right now because they don't really care what images in the robot. So you can grab those things and play with them. So you can download the source code and build them and run them yourself or whatever you want. So so that's the idea. So everything that we have for C++ and Java is all open source. It's publicly available. There's no restrictions or anything. And then the only components you need after that to be able to, and it runs on all platforms. So it runs on Linux and Windows and Mac OS. So the only thing that you need that's not, to do this stuff is a driver station and the imaging tool to get the image onto the RoboRio the first time. And those things are not cross-platform. So you need a Windows computer to do that. But then you can do all your development on anything. So I know a lot of people. I have a Mac. Austin's got a Mac. A lot of people have Linux systems. So we don't really care. And we try to be operating system agnostic, which makes a lot of work for us to be able to build and test versions for all these different computers and operating systems. But we think it's worth it. And so that's one of the things we do. Oh, the other thing I'll mention is just how many guys, does anybody do LabVIEW? Okay, so how many anyone do C++? Who does C++? Two teams? One team, one team or two teams? One team. So one team, two teams use the C++, and the rest of you guys use Java, I guess. So so it turns out that let's see, I'm trying to remember what the numbers are. So Java runs about like half? 50%? 50% of all the teams use Java. It turns out, okay, you know how there's all this stuff where people talk about like Amazon echoes and stuff, where they're like spying on you, and they, and people say, oh, they're sending everything you say when you're around them to Amazon, and they can get all, whatever's being said inside your house. And Amazon says, no, we don't do that. Well, it turns out that we spy on your robots. And so when you connect to the field, we have the stuff that sends usage data back to FIRST, and so every time you create a class, or inside the RobotBuilder program that's on the field in a competition, you create classes, you do anything, you use the cameras, like anything you want to use on the RobotBuilder, it sends that data back. So we know exactly how many people use Cantalons, and we know exactly how many there are on every robot. So we know if you added one from one next to the next on your robot, and stuff like that. So, and we use that data to try and figure out where to put our efforts, and try and spend more time and stuff, developing software. And so it's come in pretty handy. Like we know that there were 6 Jaguars last year in all of the competitions all year, because they report when they use Jaguars. So
6, just 6.
6 Jaguars, and that's it. So here are the numbers. And if you look,
Here's the chart.
is this the languages?
Languages is this.
Yeah, so here's languages. And so if you look, you'll see, so Java's running about 50%, and LabVIEW is running at?
LabVIEW's red.
LabVIEW is red. So LabVIEW is, what is this?
It's per year. It's per rookie year.
Oh. Yeah, so LabVIEW has been getting smaller, and Java's been getting bigger, and C++ is kind of holding. And then there were some people there's some teams or mentors or other people who have developed some C# and Python implementations of WPILib, where they either wrap the stuff that we have or they re-implement it themselves or something. And so there's a few people that use C++ and Java. So this is kind of interesting. I don't know if there's anything else you want to. While this is up, any curious about any other statistics? How about motor controllers? What was the
most popular motor controller is the Cantalon.
Yeah, and how many of you guys use Cantalons? Okay, what else do you use? You don't use Cantalons? The regular talons? The PWM talons? Use that. Who uses those? Okay, and Victors?
Victors.
Okay, Victors.
Sparks.
Sparks? The Sparks?
Sparks.
Okay. Yeah, so a bunch of years ago, when we first had CAN speed controllers, which was like the CAN Jaguar, I'm just going to say this since we're talking about kind of usage and stuff. We the implementation of the protocol to talk to them, right? What do you call it? Protocol.
CAN protocol.
The CAN protocol. The CAN protocol was not very good, and and things kind of didn't communicate well, and you get errors, and messages didn't get delivered, and or something didn't work, and stuff like that. And the other thing is with the Jaguars, they had that stupid phone connector, which is okay for a phone, but with data, as the thing wiggles around and connects and disconnects like really fast, it doesn't matter on a phone call, because you don't hear it. With the Jaguars, they just flaked out, when that happened. So you had really, really good solid connections, and it was kind of hard to do. Since then, working with cross-the-road electronics and the control and NI, we have much more solid connectors now that go between the RoboRio and everything else down to the power distribution board. So that problem is gone, and all the CAN stuff has been rewritten. So the CAN turns out to be a really nice way of building robots. So I don't really have a stake in cross-the-road electronics or any of that stuff, but I'll say that those things have been pretty rock solid. So if you haven't been using them, it really simplifies. It's a little bit slightly more expensive, like $10 or $20 more expensive than getting anything else. But it's but the nice thing is that you don't have to. You can daisy chain them all together, so you don't have to have a kind of star kind of topology where you run all the wires back to the RobotRio from all the speed controllers. You just loop one wire around through all the speed controllers and then back to the power distribution board, and it makes for a really reliable network. And at the same time, you get all these features of the CAN speed controllers, which you can choose to use or not use. So on our little demo robot here, we have CAN speed controllers running the motors, but we're not using any of the CAN stuff because there's no sensors connected to the controllers. But with the CAN Talons, you can connect sensors to them. So you can connect potentiometers and you can connect encoders and stuff to them. So you can just tell the Talon to drive the robot for some distance, or drive a motor for some number of degrees of rotation or some number of rotations or something, and the Talon will do it. So your code doesn't have to. So you can just say, Talon, go do this, and it'll just do it, and then it will stop when it gets there. And so that's like really nice. And so it's another advantage to using these guys. So so yeah, they're pretty nice. And so you can see that it's this one, right?
It's the pink, yeah. The pink.
Yeah, so there's this many people use CAN Talons. And
41% of motor controllers on all FRC robots are CAN Talons.
Yeah, and then what's
purple is the Victor SP, which is 15%.
So the Victor SP is really the old Talon repackaged. Okay, so both of these come from Cross the Road Electronics, and the stuff that they make, it seems to be pretty rock solid. I mean, people have not been having problems with them. What's green?
That's the Talon.
Oh, the old Talon.
Yeah, the old Talon.
Yeah, so this one is a repackaged version of this one. So actually, if you look at this thing, Cross the Road Electronics represents almost all of this, all the way to here. And what are these?
That's the Spark.
Okay.
The red is the Mind Sensors.
Okay.
And the orange is the Victor, which is the repackaged, which the Talon repackaged.
Yeah, so that's Talons also. So yeah, so the Talons are pretty nice. They're pretty indestructible. And the nice thing about them is that they don't use. You don't really need fans and stuff. You can. In fact, if you're worried, you can mount them to a chunk of metal, and and it works. Makes a big heat sink. So that's kind of nice. So what else is on here that's interesting?
That's it on this version.
Yeah. Okay. So that gives you an idea of kind of the spread of what's going on. I'll just say this now. A lot of these people say, oh, what should we use? We're like a rookie team. We're trying to decide whether we should use C++ or Java or LabVIEW. I think it really depends on the mentors that you have. The people you have that will help you make and whether they are really good at C++, or really good at Java, or really good at LabVIEW. And I mean, I think that's the most important thing is to pick a language which you can complete the program with. Where you can get help and you can make it work and stuff. But beyond that, between like C++ and Java, where we do both of them, I personally I prefer Java, and the reason is because it's a much simpler language. And if you look at some of the stuff that's going on inside of WPILib from people who are like professionals who use C++ all the time and really understand the standards and really understand how everything works, the code is like pretty crazy complicated. Not because C++ is kind of that way, and the Java code is much simpler. And the other thing is that in Java you get like runtime checking. So if you have like a subscript out of bounds, or you have a pointer reference that's wrong or something, Java catches it, stops your program, and tells you what line it happened on. On C++, you may wipe out some other part of your program because of some bad pointer or bad subscript array out of bounds or something, and you won't know it until you trip over that part of the program later. So C++ is not only harder to use, but it's harder to debug because it doesn't help you very much. So that's my personal preference. And a lot of people are concerned about Java because it's a very dynamic language and it does a lot of memory releasing and stuff like that while the program is running. But we have really had no issues from people with that, and we actually spent some time looking at it ourselves. So anyway, for what it's worth, that's what I think. You want to do the thing again? Yeah, sure.
Sure.
Is one of them better supported than the other?
No, they're all identically supported.
Are
They're all, yeah, okay, so here's what happens. So all the software, all the C++ and Java software is on GitHub, right? So it's all open source, you can see everything. And what happens is there's a bunch of developers. So there's a bunch of people at WPI, there's a couple of people, 3 people in California. I guess that's the majority of the people that do anything with it. And what they do is they work on different parts of the software. They contribute changes, and whenever we do changes, we always make the same change in Java and C++. That's a rule, so that those 2 languages, and it's really a rule amongst all 3 languages that we spend a lot of time on the phone with National Instruments and FRC and to make sure that there's parity between all the languages. So you're not at any disadvantage using any language. I mean, they all have exactly the same set of features with respect to your robot stuff. And then what you get is, beyond that, you kind of get whatever the language offers. And so whenever one of those changes comes in, somebody does what's called a pull request on GitHub. So they have a proposed change that they want to put into the code, no matter who they are, how much experience they have or anything. They put in the proposed change, and it has to be reviewed by other people, and they mark it as reviewed in Git. And so other people inspect all of the code changes, and then after that, it gets tested. So we have a test system. It's in my office. It's often very annoying. Some guests come or something, and we're talking in my office, and all of a sudden these motors start spinning by themselves and stuff. So all this stuff automatically gets routed to the test. There's a whole bunch of tests which are run over the internet in some internet servers and on our local servers, and then we have then the stuff runs on the actual hardware test system and verifies that it works. And that's identical for all the languages. So the test system for all the languages and all the tools. And all that stuff just runs in the office. So there's really no difference. And we try to not have any difference between any of the languages in terms of support or features. So you're safe with any of them. I mean, with any of the 3 languages, they're all very well supported. They do the same thing at National Instruments, except that because of restrictions that they have as a company, their stuff is not open source. So, which is, so you can't see it before the kickoff. Play with it or anything. But that's because they have their own version control system that's in-house because they do proprietary stuff and they sell it. They're trying to make money. So yeah. Any other questions? Just interrupt if you have questions because it's not the group's not that big.
Just for an example, this was something that was added a couple days ago. So this is Tyler, and he added a template for timed robot, which is one of the new 2018 features of WPILib. And then Peter reviewed it, left some comments. He went back and fixed it, and then it was merged a couple days ago. And then just to show, we have the C++ change and we have the Java change, and they're identical except for it's 2 different languages, so they look a little different.
So that's what happens. I mean, so the languages are really identical, and if you look at any of the commits to the repositories, it's always, whenever there's a Java commit, there's always a corresponding C++ commit, vice versa, so that they stay the same. Okay? So yeah, so that's what we're kind of up to. What was next? It was a 2018 features or something?
What's new for
here's what we're going to do. So we're going to look at it. This is not necessarily in order. We're going to look at the control system. So how many of you guys are like new, like you've never played with this stuff before? Okay, so there's a few guys. Okay, so we're going to talk about the control system a little bit and what all the pieces are. We're going to talk about what's new for 2018. So for all you guys who did not raise your hand about being new, then this may help you kind of see what we did for over the last summer and we're working on right now. We're going to talk about how to use WPILib to program your robot. So we're going to, we're kind of in a weird situation because our laptops have some combination of old stuff and new stuff and pre-beta stuff, and and it's sort of, so there were a few things that weren't quite working. So normally we just build the program from scratch. We'll show you the program that we wrote last night because we had to do some stuff, kind of some weird stuff that you won't have to do to get it working. And then we'll talk about using vision on robots. So for you guys who are new, for the last bunch of years, first has been, the idea is you get some field object, you pick up some object or a ball or, like whatever it is, a ball or something or a frisbee or something or other, and then you got to shoot it or put it into a goal or somehow, get it to a goal. And And in all these games, you get more points if you can do it autonomously during the first, it has been like during the first 15 seconds of the match, where the robot runs by itself. And so to make it easier to put stuff into goals, they wrap the goal with like retroreflective tape, which is this like silver tape, like highway signs. So if you put a light on your camera, I mean, you have a camera on the robot, like a little USB camera, and you put like a ring light around it, which you can get, one of these automotive tail light ring lights, which you can get for like $6 or $7. Then it lights up the retroreflective tape, and you don't see anything else in the images. And here's what the images look like. So this is an image that's like fresh off the, that we took with the camera with the ring light, and so you see stuff like this, and that's what the robot sees in that case. And so you write vision programs to do that. Here, go back to the So we're going to talk about doing vision on FRC robots, and more vision and more vision, and I guess that's it. Okay, because it's like 2 hours. So that's what we're up to. So let's go to the next thing, which I think is the 2018 stuff. Yeah. So here's what's new for 2018, and actually it's a pretty big list. It's like this big. But if you go to look at the GitHub stuff, you can see all the things which are new there also.
So that right now is published to the beta teams because it's a working document. Yeah. When we release for the season, it'll be up on Screen Steps.
Yeah. So.
But you can always find the latest changes on GitHub.
Yeah, but isn't this on?
It's on the beta Screen Steps.
Yeah, but you can get to that, right? There's no password.
Oh, there's no password. So if you look hard enough, yeah. It's up on Screen Steps. 2017.
If you go to Screen Steps. Okay, so for you guys who are new, the place where you go to find all the documentation is a thing called Screen Steps, and it's on the internet. It's called WPILib.ScreenStepsLive. That's one word. So WPILib.ScreenStepsLive.com, and you see this. Okay, and then if you look at where'd it go? Oh, down at the bottom of the page, it says 2018 beta testing. And then if you go here, you can see new for 2018. And then here's all the stuff. So here's like C++ changes and Java changes. Here, why don't you just open that up? Here, we'll just do this. That's easier. So there's some classes. So all this stuff is class-based. If you haven't been doing it, all these things are object-oriented. So there's classes in C++ and Java for all this stuff. And so we added some classes. This thing called Timed Robot. So what happened was that there's this thing called iterative robot that tries to run a loop through your program, mostly your teleapp program, every time the driver station updates the robot with joystick data and stuff like that. The joysticks are connected to the driver station, and so that was kind of a little jittery and stuff, and it wasn't always working the right way. So we had another class called Timed Robot where you can specify the time interval, like how fast that loop goes, regardless of what the driver station is setting to the robot. Sometimes people want it to go faster than the 20 millisecond update rate, and sometimes the 20 millisecond update rate was a little weird because it was taking longer, or depending on network traffic and stuff going on in your computer, it may not have been exactly 20 milliseconds, and people were counting on it being 20 milliseconds, and it and sometimes was it, sometimes wasn't, depending on what the rest of your robot was doing. So we added this time thing, which is where you can just give the time, and it uses a very accurate clock. It just measures the time for each loop. The other thing is that there's this main class called Robot Drive, which we'll show you in a little bit later. It's probably better, maybe it was better to do this in the other order, but we'll show you this Robot Drive class, which is the main class where you can put in a bunch of motor things, and you can tell the robot to do tank steering or arcade steering or mechanism, and that's been broken up to include to separate out the types of drive systems, the types of wheel chassis configurations from everything else, so that you could then add additional drive configurations. So now we have this differential drive stuff, which is for the normal differential robots, left, right wheels, differential drive for all these things, the usual stuff. Another one for 3 omni wheels and mechanism. And mechanism is what this is. It's got these mechanism wheels on it, So the robot can, translate, go in any direction and turn while it's moving and all that kind of stuff. So these are pretty cool. So it does that, and so that was that. The across the road electronics guys who provide the Victors, or provide all the Talons, wanted to change the name of them for kind of like marketing reasons or some confusion or something, I guess they thought between amongst users. So they renamed Talon SRX. What was called Talon SRX is now called PWM Talon SRX. This is the version of it that uses the PWM wires, the 3-wire connectors instead of the CAN stuff. And then they renamed CAN Talon SRX to Talon SRX. So if you notice, this is a change where you might get burned a little bit because this name is the same as that name. And so if you had a bunch of these in your existing robot code, it now changes. So you got to just be careful with that. Kind of be aware of that if you're trying to recompile your existing robot programs with the new libraries. Okay. And yeah. Okay. Let's do Java. So here's Java stuff. This is actually interesting. So we were always restricted in our use of Java, and so on the RoboRio because of Oracle, and they were like a pain. And so what we found another Java runtime library, the JRE, the Java runtime engine, from a company called Azul Systems, and it's called Zulu. It's the name of the thing. And this is a open JDK, open Java development kit version of Java. And so it's open, it's source code's available and all that stuff. But the really significant thing was that they built versions of it that work on the RoboRio. And it's open, and it doesn't have all the licensing issues that Oracle's had. So now you can we automatically deploy it when you don't have to do that step at the beginning, which is installing Java on your RoboRio with that Java installer, where it takes you to the website where Oracle has it, you download it and all that stuff. Now it just does it automatically. If you use, there's a thing called the sendable chooser, which you may get to show you later, that lets you choose between a bunch of options on the driver station, options you want to have on the robot, and it just had this problem with keeping things ordered. Yeah, let's do network tables. This whole thing, there was this whole issue. So how do you guys use network tables for stuff? Who uses? Do you use network tables?
Who uses the smart dashboard?
Okay, do you get values on the smart dashboard? Do you get to see data? Okay, so the way the data gets from the robot to the smart dashboard is through a protocol called network tables. Okay, this library called network tables. And the way it works is it's pretty cool. It's what's called it's like a distributed hash table. And what that means is that you give names for values. Like you say, I want to put X, some value called X on the smart dashboard. So you say, smart dashboard dot put data, or put number, and then you say, quote X, quote, comma, the value. And then it puts it up on the dash. So it shows up on the dashboard, which is, at the driver station. So you see it on the driver station, you don't have to be connected to the robot or anything. And you can do that for as many things as you want. And there's all this other stuff that happens automatically when you build programs with RobotBuilder. It makes other stuff show up on the dashboard. But it had this feature, or kind of the way that it worked was that it, what happens is that it caches all of the data on anything that's running network tables. So if the network table's running on a laptop, it put all the data there. If the network table's running on a robot, it put all the data there. And if one of them disconnected and then reconnected, then it said, oh, give me some, tells everyone else to give it data, when it reconnects. And all the data gets copied onto the new thing that just reconnected. And so you get these like weird errors, like, you decide to run a different program on your robot. So you download the new program onto the robot, and then you run it. And then, but lo and behold, you look at the dashboard, and it's got the data from the old program plus the data from the new program. Because the dashboard was network tables, it cached everything that was all the data that was sent to it, and I see both. Okay, so we made some changes to the way that worked. That was this this whole idea of unpredictable behavior for values. So the idea now is we change the way it does that handshaking, and hopefully it fixes the problem. And kind of like the real quick details of that are that it keeps track of which node on the network originated the data, and if that node is still around and it still does it, it populates the other ones with that data. So that's that. I think that's all of that, right? It's mostly
Yeah, that's all of it.
yeah, go ahead.
We're adding a JSON library to network tables too. Right now it's only in C++, but because we have feature parity, it will be added to Java soon.
The whole idea is that sometimes people want to send more than one value. Like you want to send a bunch of values at one time, so you make a structure, in C++, or you have a class in Java, and you want to send a bunch of values at once, and make sure they get there at the same time, and they're all synchronized. So now you can take all the data and pack them into one message, okay? And then it guarantees you either get all or nothing. So it's all there, it stays in sync. The problem that you always have with real-time programming is you send the X value, and so the robot now has a new X value and the old Y value, and it starts aiming its shooter or something based on the new value of one part and the old value of the other part, and it obviously doesn't work. So there's stuff to let you pack things into one package and then send it all at once, so you guarantee that what you have will always be in sync.
The only other change with network tables is there's a whole new API. So if you were using the raw network tables function calls before, so network tables.getTable, all of that's changed, and you have to go and look at the code examples or the documentation to find out how to use the new stuff. If you were just doing like smart dashboard.put data, you don't have to worry about that. We took care of that for you.
Okay.
Yeah.
So next is a smart dashboard. So there have been a few updates to the smart dashboard if you've been using that. So for you guys who don't know, and we'll show you this in a little bit, but if you don't know, there's a robot out in the field, but you want to be able to control it. You're controlling it with the driver station, which is behind the wall where the operators are, and so if you want to see data and stuff from it, there's this program called Smart Dashboard that lets you easily display data, back at the driver station, and that's Smart Dashboard. Well, so Smart Dashboard is kind of old. It was written for 2009 when we had the RoboRio or CRIO, which is like one version older than this thing. So that's like it's kind of getting a little bit old and long in the tooth. And so so a bunch of students have been working on this thing called Shuffleboard, which is a new Smart Dashboard, and it's based on current Java user interface libraries and stuff like that. You can skin it, so you can have the dark scheme and the light scheme and all that kind of stuff. And we'll show it to you a little bit later. But it's got a bunch of features that are kind of new. And then there's, of course, we can't forget Outline Viewer, which Austin wrote. And so this is new, and it also uses Java effects, so stuff looks a lot nicer and it works a little bit better. And this lets you look at what's inside of network tables, what all those values are, those names and values that are in network tables. And then the last thing is the Eclipse plugins. So Java and C++ are already pretty fast to deploy, but now they're like even way faster. So we've sped up the deployment of that, and part of it is that the thing has to go find the robot. There's multiple ways of connecting to the robot. So they do all this stuff. This guy in California, Peter Johnson, he's really good. He does all this stuff in parallel, so it's much quicker. And using a different protocol for sending files down, so that makes it faster. And there's a bunch of other things that were kind of done to it. Oh, the other thing is if you've used, did anybody use Net Console? You know about that?
Reallog.
Reallog, where it displays, you can do print statements in your program and they come out on the, no? Oh, right here. Okay, well, it's better now. Okay, it's easier, it connects more readily and stuff like that. So this is, if you're used to debugging programs using print statements, this is a thing that facilitates that, where you can get output, error message output, you can print stuff and things like that. And now it shows up in Eclipse as a window on the bottom. And so as soon as the program starts up, you start seeing data coming out, all of your print statements and data and stuff like that. So you have now two ways of getting data back to the driver station. One of them is the dashboard, and then the other is printing stuff in this, this console thing that's in Eclipse. Okay. Okay, what's next? So we just kind of went through all this stuff. Okay. So this is especially for people who are new, but even people who are experienced. So here's the deal. So how many of you guys use like Microsoft Word? Right? I mean, like everybody uses Microsoft Word to write papers and stuff. Okay. Forever, this is at college. In university, we have juniors. All juniors have to do a project called an IQP. It's a full-term project. They have to write a big report. It's usually like 50 or 60 or 70 pages long or something, and it has to look good. And a lot of these guys use like Word, and then they show up at a meeting with the advisors and they say, "Oh yeah, here's our new version of the report." We're kind of looking through it. We go, "Wait, but the table of contents isn't right. Like the page numbers are wrong in the table of contents." And they say, "Oh yeah, we haven't updated it yet." Okay. And well, it turns out that if you know how to use Word, okay, and you use styles and use headings and all that stuff that's in Word, it automatically makes a table of contents and it automatically keeps it up to date. Okay, but there's so many people who don't know the way that the developer intended the software to be used that they're always fighting it. And you never get the full benefit of the software that you're using. And it's the same with the WPILib tools. And so kind of the way so if you use all the tools kind of like in the way that we anticipated people using it, sometimes they do, sometimes they don't, then you get a lot of synergy, and the benefit you get is more than the benefit from any individual tool. You know what I mean? Like the sum of the parts is greater than whatever, And so if you use this, if you use the dashboard and you use the command stuff, and you can optionally use RobotBuilder, it kind of makes some of that stuff easier. Then you automatically get like a much better experience. So the way that we kind of expect people to do this stuff is that you look at your like the kickoff happens, right? And so you're on Saturday. You guys all kind of go up to Manchester, or you watch the webcast or something, and you see the kickoff and you see the game. And then like the next day you're off, trying to design robots and stuff. And so by the end of the week, you probably have some good idea of what your robot's going to look like, in that first week. And so you know that it's got a drive base, it's got an elevator, it's got like a gripper, it's got a shooter, like whatever it is. You start to have a pretty good idea about what it's got. And each of those things is a subsystem on your robot, right? I mean, that's what those are. And so the way the software works is you can when you write your program, you can first define subsystems for the robot that correspond to all of those things, and then even before you've written any other code, without writing a line of code after that, after you define the subsystems, you can use the dashboard to test the subsystems. Okay, so you don't have to write any special code to drive things or anything like that, because once you define all the subsystems and you define the motors and the sensors, and what ports they're in and all that kind of stuff, you can bring up the smart dashboard and put the robot in what's called test mode. So you see that on the driver station. That's one of the little buttons on the driver station is test. So put it into test mode, and the smart dashboard will display all of your subsystems by magic, as if by magic, and all the things which are in them. And it'll have sliders for all the motors. You can test the motor and see if it's working, and you can look at pop values. So as you adjust the, like on this thing, we have a little elevator. It goes up and down, and there's a potentiometer for that to sense the height of the elevator, and there's a potentiometer on the gripper, on the wrist, on the little gripper, so you can sense the angle of it. It's backwards. So as soon as you have the subsystems defined, you can start running all these motors and stuff, and looking at all the sensors without writing a line of code, beyond doing the subsystems. So all of a sudden, that's like pretty cool. And the other thing that's really cool is that this test mode stuff is independent of your program. So if you say the robot goes out into the field and you play a match, but it gets kind of banged up and stuff, and the operators say, the shooter stopped working. We pressed the button, the shooter motors didn't turn. And you go like, oh, what is that? Maybe a wire pulled loose, maybe there's something wrong with the code, maybe there's, whatever. you know, what you can do is pop open the dashboard, put the robot in test mode, and then you just run you can run the shooter motor to see if it works. So all of a sudden, you've now like isolated what the problem was, you know, without having to write test programs and say, oh, go to the program and say, oh, can you make it spin at half speed so we can see if it works? You know, you just drag the slider around and it just does it. And so this is like really powerful. If you create the robot with subsystems and you put in the right stuff to make it go to the dashboard, then it just does it. And then you make commands, these like simple commands, which are like what you want the robot to do. Like, so say you want the robot, in this case, for this guy, you know, we want to be able to move the wrist from horizontal to, you know, from this position to this position, or from this position back to that position, because that's what it does. And we don't move the elevator up and down, because the idea of this thing is that it's supposed to, you know, pick up a soda can or something, drive to a box, and put the thing on the box. So you can preset all those heights and all those things. And each one of those moves is called a command. And so you can make commands that do each of those simple things, okay? And then you can test them, because what happens is, for each of the commands, you'll see a button on the smart dashboard, and you click the button, and it runs the command. So you can try them all individually without writing test programs or harnesses or test fixtures or anything. The commands will just pop up on the dashboard, you just press the buttons, and it will run the commands, okay? And you go like, wow, that's like really good. And you can test everything individually to make sure that it's working. But then when you do your autonomous program, it's like more complicated, and it wants to do like a whole bunch of commands, you know, in a row. And so there's things called command groups, and you can put the simple commands into groups, and then a button will show up on the dashboard for each of the groups. And then you press the button, it will do all the commands in the group. Okay, so then you can make the robot do more complicated things. And we have a program, which we'll show you in a little bit, that does that stuff. So, so this is like really good. You can define commands, and you can test them just with the dashboard. You don't have to write special code to try each part. And the really nice thing is that the commands are independent of each other. So once you know the command is working, then you can combine it with other things and make bigger things that work. Where otherwise, if you just try and have all this code that's mushed together, you know, you never know if you change something in this part that broke the other part or anything like that. Here, everything is kind of well broken up into different pieces. So that's like a really nice thing that lets you do that. And then the next thing you can do, this is like way cool, is with one line of code, you can take the commands and associate them with buttons on your joystick or on your gamepad. So you can have a button on the joystick that shoots, which runs the shoot command, which does, you know, that may do three things, like start the motors and open a gate, then the balls fall in and it shoots them, and then it closes the gate, stops the motor or something, you know, all that stuff. So you make a bunch of little commands, make a command group that does all that stuff, and then you say, make button number 1 on the joystick do that command group. Okay, one line of code, it just does it. Okay, so, and then you can say, you can pick one of the commands and say, I wanted to do this command when the autonomous part of the program starts. Okay, so now you have an autonomous program. Okay, and that's it. I mean, so you can kind of see what I mean, where using this stuff makes it like really easy, because all the tools automatically, you know, all of a sudden start working together in ways that you probably didn't know about. And then the other thing that's really cool is when you have an autonomous command, like say the game is shooting balls into some goal somewhere. So once you get the robot to be able to shoot the balls into the goal using a camera for the autonomous program, you'd say, oh, let's do that for the teleop program too. So if the robot's ever kind of looking in the right direction, we can just press that and we'll automatically aim and shoot. Well, it's just a command. So you just take the autonomous command and put it on a button on the joystick, and then it does it. So then you get your autonomous action to happen when you press a button on the joystick. So it's pretty neat. And I'll tell you a good story is a bunch of years ago, we do these robot demos, right? You know, for like little kids and stuff. So we go to elementary schools, and we go to, you know, libraries, and like all over the place. We do like 50 of these robot demos every year. And so we were doing this demonstration where the thing was, it had to shoot balls into a goal. No, it had to hang inner tubes on a goal. That's what it was. And so there's a little piece of retroreflective tape on the little peg that it has to hang the inner tube. And we have all the kids come up, and they try and drive the robot, and they would try and get the robot to put the tube onto the goal. You know, and so this one kid came up. He was having a little bit of trouble. doing tank steering. You know how that is. Like so they're oversteering or something, and he could just never get it to work. So we said, okay, try one more time. And he like backed up the thing and got it kind of lined up. And then it turned out that on one of the joysticks, there's a button that's assigned to do the autonomous thing. So he was getting ready to start driving, and I went like this and like pressed the button when he wasn't looking. And then he started driving. But what was really happening was the autonomous command was running. And the robot was driving perfectly straight right to the goal, like it never did before when he was using it. And he's like moving the joysticks, and he probably knew that he wasn't doing it because it wasn't really doing what he was doing, but he wasn't going to tell anyone. And then it just hung the thing on the peg and then backed away. And everybody applauded, and it was like, no way he was going to admit that he didn't do that. And but then he just did it by itself, autonomously. And it's like really good, to be able to do that, to be able to take this autonomous code, just use it during teleop. Okay, so you kind of get the idea. Do you have any questions about this? So I encourage you, even if you don't, stay with it. I encourage you to at least try this stuff. Okay, maybe take an old robot or do something and just give it a shot and see if it works for you if you're not doing it right now. And I think you'll find that, and I can tell you that based on the statistics, I can tell you that all but the most experienced, well, okay, there's two ends. There's the most experienced teams who do their own thing because they understand what we did and they want to do something different, so they write their own stuff. And then there's the least experienced teams who don't know that this exists, and so they don't use it. But everyone else is using this stuff. So of the 30, is this the data?
Yeah.
Okay, wait a minute. We can see. Don't make me a liar. Right, no.
Here. You need to find the one without the team members.
Oh. So if you look at this, that's the years. Wait, where's any of the command things?
Yeah. It's here. Here.
Yeah. Okay. So if you look at this, the ones that say command are the ones who are using the command-based framework. So if you look at them, of the C++ and Java teams, most of them are using it. And then, like I said, the ones that the real high-end teams, like 971, like they do their own thing. And then the other teams that who don't know that this exists don't use it. So, but otherwise, everyone's using it. Yes. No. So the way it works is it's really just a class that you write. And you put some code into the class that says what it should do when it's executed. And you can have as many of those as you want. And you just put them into a bunch of command groups. And that's it. And so there's no limit. It can be as long as you want. You do some really, it's like in whatever the year was with the pyramids, you had to climb the pyramids. We had this like crazy complicated sequence in our robot. I don't know why, but the mechanics were such that it had to do like a whole bunch of steps to make it autonomously climb from one run to the next one. So the idea was we wanted to be able to press a button and have the robot do all this stuff to get up to the next run, which was like a ton of stuff. And we just made it a command. You press the button and it goes up to the next one. It does all these things. It looked really cool, like people thought we were doing it, but the software was doing it. So yeah, no limit. Any other questions? Yes.
There's no way.
Nope. No, you can mask them arbitrarily. It doesn't. All it's really doing is there's this loop, right? So when the program is running, it's looping. They either do that 20 millisecond thing or doing something with your timing. And every time the program loops, it goes to all the commands which are currently running and says, do your stuff. And it does a little bit of stuff, and then it returns, and then it loops again. It just keeps doing that over and over again. It doesn't matter how many you got. People could. But the other really cool thing about the commands is you can have multiple commands running at the same time, because it just says, I want to be running this command, and this command all at the same time. So you'll see. Oh, maybe you won't see it. Did you do it on here when you made it? Did you make parallel? Yep. Yeah. So I'll show you on here when we get there. Okay. So that's this stuff. So give it a try. Okay. Don't be those guys that that use Microsoft Word and don't and create the table of contents manually. Yes.
How do you do this? Is there like manual?
Yeah. There's lots of documentation and screen steps, and there's a program which we'll show you in a minute called RobotBuilder, And what it does is it creates the skeleton of the application. It doesn't, obviously can't write the code for you. It doesn't know whether you have a shooter or a Frisbee launcher or a ball collector or anything like that, but it can create the classes for you that correspond to all of your commands and all of your subsystems. And then you have to fill in what they do because it can't know what they do. And it will actually create all those classes for you, and then and it can also wire them together like the joystick buttons. It can do that for you. And the interesting thing that it does that makes it easy is it generates the magic one-line function for subsystems and commands that gets them up onto the dashboard. So you don't have to worry about that. You can do it all by hand. And in fact, last night we were doing this thing till midnight or 12:30 or something last night. It was pretty crazy. And we were trying to get around some bug that we had and fix another bug. And so we started using the RobotBuilder, then we just stopped and then just started doing the stuff by hand. But normally you can just use it throughout the whole build cycle. And by the way, there's so like I said, we're not going to be able to show you this whole thing now, but there's a video. I'll show you where those are later. But there's a video that's up that basically walks through every step, nothing unseen, to program this robot to do this pretty complicated autonomous stuff and teleapp stuff. So you can watch that, or have, students can watch it, or mentors can watch it, or anything. And you see every line of code. You know how like you watch cooking shows and they do some stuff and they put the turkey in the oven and they pull it out like a minute later and it doesn't look anything like the turkey they put in the oven. It looks much better. And you go like, how'd they do that? Okay, well, we don't do any of that stuff. I mean, you see every line of code that we type to make the thing work, and in the video, and it takes like an hour, and then it programs this thing to do something which is kind of what an average FRC team does for the whole season, and we do it in an hour. Now we've rehearsed it, so you may not do it in an hour, and we wouldn't do it in an hour the first time we tried it, but you get the idea. Yeah.
With this RobotBuilder, it's easy then to also add new elements or Yeah, so what you can do is suppose that the first thing that pops out is the chassis, okay, and you want to get people driving it, with a camera on it or something, so you can practice doing the autonomous vision thing or whatever. Then you can just write this, you have the subsystems for the chassis, and you make some commands for the chassis, and you start going. Then you just add more commands as you go. You say, oh, now I got a shooter, and then maybe. After your first district event, you watch what everyone else is doing, and you go, oh, we really need floor pickup, for whatever it is, for the balls. And so you add some floor pickup thing, just add some commands. Add the subsystem, add some commands, and you get that. Okay? So it's pretty easy. Okay. So if you don't get anything else, get this. I mean, get this message and give this a try. Okay? And I think you'll find your life will be much happier. Okay, what's next? Oh, this is RobotBuilder. It looks like this, and these are all. Here's subsystems. Here's controllers. Here's sensors. So basically, the way you do this is if you look, you come over here and you define all these things. So here's like a drivetrain subsystem and a collector subsystem and a shooter subsystem.
I'll just open it.
Oh, you do the real one.
Yeah.
Oh, with the real program. So all this stuff is in the tools directory after you install the Eclipse plugins. So you go there. So here's all the here's some subsystems like a drive base, a claw, an elevator, a wrist. Here's the operator interface stuff. And here's a few commands that Austin defined in RobotBuilder before he stopped using RobotBuilder because of this bug that we found. And so you can see that you can either right-click on subsystems or something. Well, you can right-click, and so here's a drive-based subsystem, so you can just choose what you want to add to that subsystem, like what sensors and motors are part of the subsystem, and you do that, or you can drag them in from here. So like the Ninja guys, just right-click and it pops in, but if you're not sure exactly what to do, you just go and paint by numbers, just dragging stuff in from the palette on the side. And these are commands. This is like a command group, and it does it graphically. So you can say, I want to have a group, and here's the start of the group, of the things in the group, and here's a command. Then you can add more commands, so you just drag them in, and it makes these command groups of things that have to happen sequentially, okay, or in parallel. So you can do all that stuff just by dragging stuff in.
So it's, dragging commands in. So that's pretty neat. Okay, so RobotBuilder helps you do this. A lot of people say, oh, if I use RobotBuilder and it generates code, it generates your project, right? It generates the classes that are in your project. And a lot of people say, oh, yeah, but what if I want to make changes? Then how can I keep using RobotBuilder? And it turns out that the way RobotBuilder generates the code is the stuff that it generates, it puts inside of these kind of comment blocks. So there's a comment above it and a comment below it. And that's the stuff that gets auto-generated. And everything else in the file you can mess around with. So you can extend everything else that's there. And that's where you put your code. And then every time you rerun RobotBuilder, it only changes the stuff that's in between the comments. So if you add a sensor to a subsystem, or if you add something else, you can do that. It doesn't matter as long as you don't change the stuff between the start and end RobotBuilder comments. Oh, here's some. She says begin auto-generated code, end auto-generated code. So just don't put anything. Don't mess with the stuff that's in between there, because that's RobotBuilder generated. And everything that's outside of these things, these begin and end blocks, you can put in yourself. So, okay, is everybody okay? Any questions yet right now? What should we done? Oh, it must be at 11:30 or something. We're done. 11:30. What? 11. 12 with this? Okay. Okay. So that's RobotBuilder.
It's not there.
What's next?
We're going to go over the control system.
Yeah, so let's go. We'll do this is going to be like a literally whirlwind tour of the control system, because a lot of you guys are pretty familiar with it. So back in 2000 and when was it? 13, 14?
15 was the
15 was the RoboRio was introduced. It was a new controller. It's this thing here. It's the gray box on top of the robot. So if you haven't done this before, so you don't have a kit, you can come up and look at this one. You can see it. It's up on. It's like this big. And this is it. It's a dual core ARM Cortex, which means it's like about the speed of a like 6-year-old cell phone or something, and which is fine because it's plenty fast for this. And then, but the other thing that's really nice about it is that for some of the stuff it has to run fast. Like you want to count encoder counts, and you want to do analog sampling, and you want analog value sampling, you want to do stuff like that. There's hardware built into this called an FPGA, a field programmable gate array. And what happens is that we configure that to be able to handle all the sensors that are used in WPILib. And so it all does that. That's all done in hardware. So you don't have your code doesn't have to be fast to do that stuff. It just has to be able to read the value back from the FPGA. So if you have an encoder going, it's returning thousands of counts, like per second. It doesn't matter if your program can't keep up with it. All it's going to do is ask the FPGA for the current value of the encoder, and it's going to return it. So that's like really nice. It has SPI, Ethernet. So this is for communications, like a serial communications protocol. Ethernet is Ethernet. It's got USB host, so you can plug in like flash drives and stuff. So one way sometimes people put stuff onto the RoboRios, they put stuff on a flash drive on their laptop, and they plug it in, and you can plug it in here and copy it. There's a USB device protocol port, and this is, so you can take a USB cable and plug it into there, get one end in there, and the other end into like a Windows laptop. And you can use that instead of a network connection. So it's sometimes easier to connect with USB port than using Wi-Fi or using the Ethernet connector. Power, here's the two CAN connectors. The CAN connectors are these little things where you push them down, and the little hole opens up, and you stick the wire in it, you let go, and that grabs it. And so those are really reliable. Here's I2C, which is another serial communications protocol. RS-232, which is another communications protocol. Here's all the digital I/O over here. Here's the analog I/O over here. And this is where you plug in the robot signal light, the flashing RSL light that tells what state the robot is in. So when the FTAs are looking at it, they know whether it's, the code is running or not running and what's going on. And these are the PWM ports. Back in the olden times, all the motor controllers used PWM signals, pulse width modulation signals, to drive them. But now, like you saw in the chart, everyone's starting to flip the CAN. But these are these are PWM controls for controlling servos or controlling regular Victors or regular Talons, not the CAN stuff. Okay, this is the power distribution board, power distribution panel for Duke. So it's got channels 1 through 8 here, channel 16 through 9 over, or 9 through 16 over here, and this is where you plug in all of your motors and all the stuff which is that needs electricity, needs power.
So what's cool about the power distribution panel is if you look at it, it also has CAN. So most likely when you read the rules, there will probably be a rule that says you have to plug the RobotRio CAN into the power distribution panel CAN. And what that lets you do is it lets you read the voltages or the voltage that you're getting from the battery. So you can look at the driver station and say, oh, I have a low voltage battery. It's time for me to switch. It also lets you do fancy things like monitor the current that you're drawing on every channel. So you can tell if a motor is stalled by saying, oh, it's drawing a lot of current right now. It's probably stalled.
Yeah, it's pretty cool. So, and all the stuff gets logged in the driver station. So you can see every one of these channels. So if the robot nods out in the middle of a match, you can look at it and you can say, oh, that was channel 4 where it was drawing too much current and stuff, and you can kind of figure out what's going on. Like maybe a motor stalls or something, so it draws a lot of current, so it takes the voltage sags down. So you can see that which motor is drawing all the current, and you can look at that in the graph that's in the driver station. So that's pretty cool. This thing is this pneumatics control module. How do you guys use pneumatics? A few. Pneumatics is like this very underused thing. Pneumatics is really nice for stuff, especially for things like a claw where you want it to close and you want it to maintain pressure, but you don't want to, for lifting something, but you don't want to keep the motor running because it's going to stall and get hot and stuff like that. Well, pneumatics doesn't care. You just tell the claw to close using some pneumatics thing, right? Air pressure with a cylinder, and it just keeps applying pressure, and it doesn't care how long you want it to before nothing overheats. And it's good for a lot of other mechanisms that are really, really well suited to some linear action thing, which motors don't easily develop. And so pneumatics works really well. But the reason people don't want to use pneumatics is they say, oh, we have to have the weight of the compressor on our robot. But if you put the compressor on the robot and then you find 2 or 3 subsystems that want to use pneumatics, then you've made up by taking off all those motors and putting on lighter actuators for pneumatics. You've made up for the difference in the weight, and then now you've got pneumatics on your robot. So that's pretty cool. So that controls all the actuators. That module controls all the actuators in pneumatics. This is the voltage regulator module. This thing is designed so that you can put battery power in, and it generates very, very accurately regulated 12 volts and 5 volts. And the thing that's really cool about it is all of these outputs are isolated from each other. So if one of them, there's a video that the guy who designed this made where he takes one of them and just shorts it, okay, and then it maintains the voltage on all the other ones. So they're all very independent of each other. They're very good if the battery voltage starts sagging, and because of that, like you have to connect your radio to this thing because it's a 12-volt supply for the radio because if the radio nods out when you start drawing a lot of current on one of the motors, then it loses communications with the field, and the radio takes like 40 seconds or something to reboot. So you don't want to, if you're in a 2-minute match and you go away for 40 seconds, it's like really annoying. So
talking about the radio.
Yeah, talking about the radio. Here's the radio. It's from Open Mesh. There's a new version of it this year.
Last year.
Huh?
Last year.
Last year. Right. There's a new version of it last year, and so it's connected to the Ethernet port in the RobotRio. It's got 2 Ethernet ports, so you can plug in a camera, or you can use the other port for debugging, or something like that into the other port. If you need more than 2, you can just stick a cheap switch, on the robot that runs off 12 volts, and then plug it into the voltage regulator module. Okay.
More than 2, 1.
Oh, more than 2 Ethernet ports. Okay, so sometimes people have like a camera. Well, okay, sometimes they have a Raspberry Pi, and then they have the RobotRio plugged into this thing, and now all the ports are gone. But they want another port to be able to connect to a laptop to debug things or something like that. So you can put a switch on the robot if you want, or you can unplug the Raspberry Pi and plug the thing in.
These things are notorious. This power connector is terrible.
Yeah, oh, yeah.
So
That's a really good point. Okay, so here's the deal. Yeah, the power connector, it's the barrel connector. You know, like one of those connectors you see on, well, there's one up here, you can see it later. And so the little connector is not made to be put on a robot. Okay, and especially not last year, the year before, when robots are driving over those defenses and they're like bouncing around like crazy, those connectors kept popping out. Or they just pop up for a second, then they pop back in again. Okay, and then the radio would stop working. So if you watch those matches, there were more robots that were failing in the middle of the match than any other year because they were bouncing around so much. But even in regular matches, if you see a robot stop moving on the field, if you watch closely, 90% of the time that will happen after it smashes into something. So it'll smash into the wall or smash into another robot or something, and then the robot stops for 20 seconds if it's rebooting the robo-reel, or it stops for 40 seconds if it's rebooting the radio. And you got to really, really be careful with these things. So you got to like secure the power connector to this with like tie wraps or something, zip ties, you know, because you don't want it to pop out. Yes.
There's DOE capability now as well.
yes.
Power over
So obviously the rules for 2018 have not come out yet, but in 2017 you were allowed to use passive injectors for the open mesh radio, and all that means is you would like take apart an Ethernet cable, find the wires that let you apply power to the radio, and apply power that way. But be very careful when doing that, because if you accidentally apply power to the robo-rio, you're $400 out and have to buy a new robo-rio. So yeah, word of the wise.
But just make sure that the connector is secure.
Yeah.
We don't do that stuff. Yes. Well, I'm
Yeah,
saying,
so-
yeah, and really, you can use tape, but really, you know, don't use tape. Tape, the adhesives, you know, like come loose. You know, I mean, tape, it's tape. You know, it's not designed to be a structural member of the robot. So use like a, you know, zip tie wraps or something.
What some people do, and you can look on some forums online that might have orange colors on them. They have 3D cases, housings for the radio, and on the 3D housing, it's sized perfectly. So there's a wall that just does this to the connector, and you can't remove the connector without pulling the radio out of the housing.
So do something like
Do
that.
something
just to make
like that.
sure, you know, that all the wires are secure. I'm just going to mention, while we're talking about it, I'm just going to mention, and Austin, who's on the field all the time, can also tell stories about this, but very often, robots stop. The team comes up to the FTA, you know, on the field, the first tech advisor, and says, "Oh, your field is broken. My robot stopped in the middle of the match." And then they walk over to the robot, and there's the power connectors, you know, that's on the power distribution board, those big thick wires. And then we say, "Oh, grab that wire and try moving it." And it turns out if you can move that thing at all, okay, then during a heavy hit with the robot, it's going to move and disconnect. So even if the nut doesn't pop off and the wire doesn't pop off of the connector, if you can grab that thing and you can rotate it by hand at all, it will cause the thing to reboot when it's hit hard. And he can tell you lots and lots of other stories about things just like that, where people say, "Oh, it couldn't be our robot," but then it turns out it's a loose wire somewhere. So you got to be really, really careful about crimps. You have to be really, really careful about all that stuff, or you'll be very unhappy. And you know, because you figure, you know, you get like 20 matches or something during a season, you know, for the registration fee. So each match is, is like $500. You know, so you don't want to have the robot stop in the middle of one of your $500 matches because somebody didn't crimp a connector correctly. So you know, after you crimp connectors, yank on them, and you put the screws into the battery, or you put you connect the wires to the battery or the wires to the power distribution board. Make sure you can't move them, that they're really cinched down tight, and all that stuff. It's not just the radios. It's like all the heavy power stuff is like constantly breaking. Even on Einstein, we see that. You know, on the final matches of the World Championship, we see robots that stop in the middle of the match because of some power connector, you know, loose wire or something. Okay. Yeah, this is a typical wiring diagram, which you can't read. But if you look on, because it's too small, but if you look on screen steps, then your glasses won't help. So if you go on screen steps, you can see this like much better. But it really just shows how everything's connected to everything else, and you can kind of look at that and see how it's supposed to work if you haven't done this before. These are the speed controllers. Oh, there's 2017 speed controllers, which are the same as the 2018 speed controller. So there's actually, I don't know what's announced. There's the Victor SP.
They announced it.
Did they? Okay, so there's these are the two popular ones we were talking about, which were the big wedges on the pie before. So there's a Victor SP. This uses PWM control, and this replaces the Victors, the old Victors, and the old Talon SR. And then this is the CAN one, and this has these CAN wires that come out where you daisy chain them together between, from one motor speed controller to the next one. And this is the one that, and this one has, it's hard to see, but somewhere on here, there's a little connector, and you can plug sensors into it. Be aware, if you use this and you want to plug sensors into it, it doesn't come with the cable you need to connect the sensors. So there's a bunch of sources of these cables. You have to go buy the cable separately, either from Cross-Road Electronics or
AndyMark.
AndyMark has one that I like much better than the Cross-the-Road version. That just has PWM connectors on it, so you can just plug stuff in that's like what you're used to plugging in. The same wire you use for the rest of the robot. But the other ones are fine too. So you can either get it from Cross-the-Road or from AndyMark, and it does that. And then there are a couple of others. What am I missing? So there's the Spark.
So there's the Spark, which is the motor controller that's included in the kit parts. So all of our examples use the Spark. There's the Mind Sensors motor controller, which I don't see quite often, so it might be hard to acquire. And then there's some new motor controller coming out this year, combined motor and motor controller, which you can read more about because I don't want to say too much on the FRC blog. So if you go and you read the FRC blog, there's this brand new motor controller, motor combo, and read more about it there. But it's very cool. We're all very excited about it. Definitely play with it if you get one.
What is it called?
Check the FRC blog. Yeah. Actually, here. See.
Sometimes when we're writing the software for stuff, we find out things before it's published, and we want to make sure that what we say is what they said, not stuff that we happen to know from some other place.
This is what it's called.
Oh yeah, NIDEC.
So yes, there's lots of links here. Obviously, it's really easy to get to because I just Googled FRC blog and it popped up. But you can read more about it here.
The other thing about this is it's a brushless motor controller. So all the motors, or brushless motor. So all the other motors which we've been using forever since 1992 are all brushed motors. And brushless motors are actually what people use these days for real applications. And they're pretty nice. And so we haven't had any experience with it, but it's got a lot of potential, for being a really nice, motor. If you see all those, like, all the little quad rotor motors, go buy a quad rotor, those are all brushless motors. And they need special speed controllers to operate them.
So obviously we have all the three languages, Java, C++, LabVIEW. The RoboRio itself is a Linux operating system. So if you want to do your own thing with that, you can. It's available. Not many people do that though. Like one team, I think.
Okay.
Yep.
So if you use Linux, if you use Linux, ever use Linux? Like have it on your laptop or something? Yeah. So if you're like a Linux person, since it's Linux on the RoboRio, you can just SSH to the RoboRio. It means you can connect to it with a terminal and you can type in commands and you can see what's going on, and you can install other packages, software packages onto the RoboRio and all that kind of stuff. I mean, we don't guarantee that there's compatibility, but you can try all that stuff and play around with it. And you can, if you really break it, you can always just re-image it and you get back to the starting configuration.
Yeah.
What's Valgrind?
Oh, What's it? Oh, yeah. So Valgrind is a tool that lets you look for memory leaks and stuff. Okay, for like C++ programs. So it's like a memory leak checker. Java doesn't do that. Java doesn't need it because the way it manages memory, you can have memory leaks, but you can't have bad pointer references or all that kind of stuff, which Valgrind will find because it's the way that Java works. It's like it's a simpler model for pointers to data. So there's the tools. You get there's the dashboard. So we'll talk about Shuffleboard in a minute, but there's the old the smart dashboard, which is, and depending on how well Shuffleboard works when it's time, come January, the smart dashboard still may be the dashboard of choice, but people can play with Shuffleboard now. I mean, you can download it, you can play with it right now and run it and see where it is. And it keeps, there's several pull requests per day on it. So it's changing like every couple hours. There's an imaging tool, which is the thing that you need that only runs on Windows. It's a LabVIEW program that lets you copy the RoboRio image onto, load it.
Mm-hmm.
It's called RoboRio tool or RoboRio imaging tool. It's this thing. And this thing finds RoboRios on the network. It lets you pick an image. So here's an image, FRC RoboRio _2018 v9.zip. So that's the image. And it will let you blast it onto the RoboRio. So that just re-images it from scratch. It's like you take your iPhone or Android phone or something, and you just reload all the firmware. It's that. And so whatever you had on it goes away, and you have to put it back again. Okay. And then there's, the robot simulator is, so the robots, we haven't been able to, the robot simulator is kind of like a unhappy story. We did this thing that was based on a tool called Gazebo, which is a high-fidelity robot simulator. And the idea was you could take your robot programs and run them in Gazebo. So you take your robot model and put it into Gazebo. And you can see the model, your robot model. You'll see a thing that looks like your robot connected to your robot program running on a Windows system or running on your running on a computer, and it operates the robot in simulation. You see all the things moving and all that stuff. The problem is that it never got ported to Windows, and so we kind of have not been spending time with it because if you use SolidWorks to build your robot, for instance, that's what we were importing, the models that we were importing. You take a SolidWorks model and port it into the simulator. You have to run SolidWorks on Windows, and you have to flip the computer to Linux, and you have to take the model and put it into Gazebo. And then you find out that you made a stupid mistake in the model, so you have to go back and reboot Windows, and you're like back and forth and back and forth. It was like a pain in the neck, and it was kind of like not an easy install to get all the stuff working. And so the guys who did the simulator kind of promised us for a couple of years that they'd have a Windows version, but they ended up doing other stuff instead, so we never got the Windows version of the simulator.
We're working on a new simulator.
So we're working on a different style of simulator, which is not a high-fidelity simulator, but it can let you see what's going on in your robot program and run it on Windows. Development tools.
We'll show you that when we do the demo.
Yeah. So everything is based on Eclipse, which is a industrial strength development tool that people use. So for writing real programs. Okay. The development tools. There's no licenses except for the driver station, the imaging tool. There's no, and then you get from NI. No license, everything open source. RobotBuilder, Shuffleboard, Grip, all open source. Here's what Shuffleboard looks like. So what you see over here on the left is all of this is everything that's in network tables. So you see these values, like here's a PID controller. Okay, here's a subsystem, which is a PID subsystem, which means it's got a PID controller built into the subsystem. And we'll use that in a minute. But you can see the name of the subsystem, and you can see the P, I, and D values, and a set point, and stuff like that over here. This is what's in network tables in this little tree display. But then you also see it over here graphically. So here's one of those PID subsystems, like this one, and you can see the same data that's here. And this is actually going to look a little bit better, and it looks a lot nicer right now on the smart dashboard, but this is going to improve on Shuffleboard. So you get to see all that stuff in real time, and you can manipulate the values of the. You can change the PI and D values, and then see how the thing works. You can set and then set the set point, you know, to move the arm up here, and then enable it, and you'll see the arms go up. And then you can say, oh, that was like too fast or too slow. We'll change the proportional control value, and then you do it again, and it works. Okay, so you can tune the PID controllers using that. Oh, the other thing that's really cool about it is that it has record playback. So we're still working on this, but the idea is that you go do a 2-minute match or a 2-minute, 15-second match or something, and it will record everything that happened, all these values that showed up. Okay, and then when you get, and if something didn't work in the middle of the match, like say at the end of 1 minute something wasn't working right, you can go back and rewind it to where it was at that time, and you can look at all the values that were in network tables, so you can see what was going on at 1 minute and see why the thing wasn't working. Like maybe you'll see that, you know, some voltage was wrong or something else was wrong, and or the camera really wasn't looking at the target, or the driver said that he was turning left, but if you look at the thing, it was really turning right. You know, you can see all those values. So it's pretty cool to be able to kind of, you know, like a TiVo, you can just slide the cursor around and be able to see all the stuff which is happening on the robot at any time during the last run. Okay, for computer vision, okay, and like I said, every year for a long time, first has been making the games computer vision friendly. We use OpenCV, which is Open Computer Vision Library. It's an open source industry standard computer vision library. So if you go to a university, for instance, everybody uses OpenCV. I mean, this is like, you know, if you go to a university or you go look at a lot of company stuff, the OpenCV is far above the most prevalent standard library. And there's tons of books and videos, and you can learn all about it and stuff. What's next? So here's like an OpenCV program. This is a bunch of years ago. There were 2 goals. You know, they had a little U-shaped pressure reflective tape underneath them. So this is the thing which we were saying with the camera, where you have a ring light around the camera that lights up these things, and then you turn the sensitivity way down on the camera. So all you see is these, and in this case, are these annoying purple lights that went up the middle of the castle that had these things on it. And so you can write a program that tune for the colors of the goals, and this is happens to be a Python program, you know, which you can run on like a Raspberry Pi or something. But this is the entire program which finds these things and prints out where they are, like relative to the camera view. And you can say, oh, it was like 20 degrees offset from the center of the camera, so we got to turn to 20 degrees, you know, to shoot that thing or something. And so you can make your program do it. So it's pretty, I mean, it's not very complicated. It really just does some stuff where it takes the colors of this and tries to make filters that narrow it down to those colors, and then it looks for what are called contours that represent those things that it found, and then you can just see how many there are, and you can see how big they are, so you can probably get rid of all the noise. So we'll show you that in a little bit. But there's another way of doing this, which is really nice, and it's called grip. And this was at WPI, all the seniors have to do a capstone project that's in their major. And so a couple of CS and RVE major students 2 years ago did this thing called grip. And it's a graphical vision pipeline creation tool. So the way vision programs work is you get the image and you do something to it, like maybe you scale it. And then you do something else to it, like you filter it for, you know, certain colors, color ranges. And you do something else to it, like find the contours. And you do something else to it, and you have a whole bunch of steps. So there's this pipeline. And what it lets you do is from a palette, grab the OpenCV steps, drag them on here, and then just connect one image to the next image with wires. And it creates a vision program for you. And when you click on the little things here, which you can't see, that say show the image, it actually shows you a picture at that step of what the thing looks like, so you can see if it's working. And if we have time, we'll do that. So that's open source. You can just download it. It's on GitHub. So if you look for grip, you search for grip and WPI or something, you'll find it. It'll be the first hit in Google. And then here it is. And if you scroll down a little bit, it says down here somewhere where to get it. Oh, release. See, it says newest.
It's right here.
Oh, there it is. Releases. So here's the releases, and you can just go and find the one you want. So here's the Linux version, the Mac version, the Windows version. So you can just download the version you want, and you can run it on your laptop. Oh, and this is another important safety tip, just like those other ones at the beginning. What we do every year, you know those kickoff videos that you see where you see these guys like walking around the field and explaining the game and all that kind of stuff? So those videos are made like a month before the kickoff or 3 weeks before the kickoff. And what happens is the field gets set up in a double top secret location where you have to have a double top secret person to go inside and see it. What we do is we go inside there at that time and we get a camera with a ring light and we take hundreds of pictures of the field just like they'll look when you on your robot. Okay? And then at noon on the kickoff day, they pop up. They're on the website, and you can download them. And so what that means is that you can go home at noon after the kickoff with a laptop, and you can write your vision program for your robot using those images. Okay? So you get like 90% of the way done on the first Saturday after the kickoff without having a robot, without having a camera, without having a RoboReel, like without anything. And you can use grip, or you can write the stuff by hand, and you can get the vision stuff working. And then when you finally get your stuff all together and it's working, then you just have to tweak it a little bit for your camera and the color of the light, like whatever. But you now have tested it with hundreds of images. So you try an image, see if it works, and you go, oh, it's working, it's great. Then you go to the next image, and maybe that one's working. You go to the next image, and maybe that one's not working. So you tweak some of the parameters on a filter, and you go back and try them again. And you just keep doing it until you can see all the images you care about, that it recognizes.
Is there a question in the back?
Oh, they're on.
We take them. We store them on a site called CollabNet, but the link is on ScreenSteps.
Yeah,
so
if you go to ScreenSteps, it will tell you where the images are. And you can actually, if you want to play with it, you can set the images from last year or the year before or the year before that, and you can play with it. Where's those?
Right here.
So if you go down here in ScreenSteps, it says here it is. Here's all the here's a grip project. A description of how you do this stuff, and all the example images in a zip file. So you just download this, and you can practice with it right now with last year's game, or the 2016 game or the 2015 game, because we did it for all of them, and you get a big head start. Yes. Wait, why is the vision program what? Why is the vision program important? Oh, yeah. Well,
so a little bit on that. We'll use this past year as an example. So this past year, you had to shoot the fuel into the boiler. Here, I can pull up a picture of the field. But you had to shoot towards the driver's station, and it's really hard to line up when you're facing yourself because you can't see where the robot's pointing, and it's really hard to line up when you can't even touch the controls because you're in the autonomous mode. So it's impossible. So what teams do is you look at the target, and you have to be able to process the image in some way to figure out where the robot is relative to the goal. So you take a picture and you say, oh, I'm pointed 15 degrees to the left, so I better turn 15 degrees to the right in order to line up. So the fuel goes into the boiler. The wiffle balls go into the goal.
Okay. So you use it to line up at the goals to be able to score the field objects, right? Because all the games work that way. Every year the game is like that. Where there's some field object, you have to score it in a goal of some shape. And the goal is always kind of annotated with this retroreflective tape. And so you do vision processing, and then the robot can find it either during the autonomous or teleop periods. Does that make sense? You get that? Okay, good. Anyone else have any questions? Don't be shy. No? Okay.
I have a question.
Yeah.
Last year there was a, developer with gears.
Mm-hmm.
There was 2 separate images on each side of the gear.
Oh, 2 pieces of tape?
2 pieces of tape.
Yes.
Yeah, these two.
Yeah. So here's
That.
an image this is from the set of images from last year. So here's one of them, and there's a whole bunch of them, and you can look at them. But this is what the robot sees. And so the idea was that you would find these two images, you find this and this, you know, two things that are about this size and about that wide, you know, and it has the right aspect ratio, and it's the, you know, and the ratio between this one and this one are correct, so you know that it's really these two targets. And then you got to put the balls right here.
Right in the middle.
Or put the gear right here, right in the middle, at a known height. So you just aim for this thing, and then you can deliver the gear.
Does that make sense?
Does this grip allow you to handle two separate
So what
pieces and somehow put them together?
what grip will do is it'll take this image and it'll say, I found two blobs at these two locations, and they have these widths and these heights. And then what you have to do is you have to go and say, oh, if the widths are of the two bars are the same and the heights are the same, then I've found the target and I want to take whatever X positions they are and find the middle of them.
So it's going to give you two separate.
Yes,
Yes.
two results.
After, I can show you the data that it'll produce from this image.
Yes.
Yeah.
So if you're
Yep. Yep.
Yep.
Yeah, yeah.
You have to handle that.
That's for you guys who take trig in school, get to use your stuff, okay? Because it's skewed, exactly like you're saying. So there's a little bit of parallax, and so one, they're different sizes, or they're different, or maybe it's not a rectangle, it's like a parallelogram with the top and the bottom kind of skewed a little bit. So you do math stuff. It's amazing. It works outside of class just the way it works inside of class. So you can do all those things that you did in your math class on the robot. So if Dean were here, he would say, yeah, that's the point of all of this. So, yes. Mhm. Yes. Yeah, you can. So you can take the camera, and you can, with grip, for instance, you add a source. See over here it says sources and head source. So you add a source, which is the camera, and then it will grab the camera screen. Okay. The other thing you can do with grip is, well, here. So Austin just loaded up all these images from the directory that had all the images in it. So here, I'll show the image first. So this is the image that it's seeing. Okay, and if you click these arrows, it goes between all the images, and so he actually selected, like, you know, a couple dozen images or something. So now if he clicks the arrows, it goes through all the images, because you want to not be able to make it work for only one picture. You want to make it work for all the pictures. So you have to kind of mess around with it. So now he's doing what's called an HSV threshold, hue saturation value threshold. So he's trying to find values of these three sliders that only show the targets. And in this case, it's mostly value. Okay, so as soon as he gets the value right, you go, whoa, look at that, the target just popped out. And it's the only thing that's it's in the picture. So now what he can do is tell it to find contours. So he dragged the find contours block and turned it on. And now you can see contours that represent the images. Okay, now they're not quite continuous. And if you're scrolling down, you can see the number of contours.
No, found 4.
So I found 4 contours. And there's really 2 things there. So there's tricks you can do to make it so that it connects those lines together that aren't connected, so you really only get 2 images and 2 contours. So now it's finding the 2 contours. So you can click color contours. That one's red, that one's yellow. And by putting it into this filter. And in the filter, you can say what the minimum area is, and the maximum area, and the minimum width, and the minimum, maximum height, and all that kind of stuff. And you can mess around with this filter and pick things, and then you drag the contours to a network tables published contours report, okay? And it puts the values of where those 2 things are into network tables, and then your robot program goes, oh, get me the X, get me the Y, get me the X, get me the Y. That's where the 2 things are, and it aims for them. Yes. Yeah. Well, you can either look at the output or not, or ignore it. So if it's at a time when you don't want to, so you can have it constantly looking, and it'll just keep telling you whether or not it sees a target. And the robot says, oh, there's nothing there, there's nothing, I'll do something else, there's nothing there, I'll do something else. Like whatever it is. And so you can wait till you see the thing and then shoot or line up with it or something. Okay? Yeah.
What's the output of this?
So
This is the output.
No. You don't want this.
Oh,
well, okay,
yeah,
all right. So
sorry.
we'll talk about this in a minute. So save that. We'll talk about that in a minute. But basically, in this case, the output is in network tables, and here's the outline viewer. Okay, and you can here's all the center X, center Y, the solidity, the area, the height, and the width, and so there's two values because it found two blocks. So here's the center X for the first one, and center X for the second one, the center Y, and the center Y. And what you do is you take the camera and you figure out how many pixels wide the camera is, and then you say, oh, it's off by 5 pixels, and you can figure out the field of view just by measuring it, like with a tape measure, and somebody walks out in front of the camera. You figure out the angle of the field of view, and then you can say, well, each picture is worth, each pixel, is worth like 2 degrees. And then you can say, oh, we're like, the thing was like, at this X value, 203, and maybe the thing was 400 pixels wide, so it's off by 3, which means you have to turn 3 times 2, 6 degrees to the left or something. Okay, so you just do that math. So it's not free. It doesn't do it for you. It doesn't like drive your robot into the target and shoot, but it gets you way close to being able to do that. Yeah.
It's 11.
Oh yeah, sure. You want to take a break for a couple of minutes? Yeah, why don't you do like a 5-minute break? But come back because we got a lot more stuff. And if you want to come up and look at this thing, it's sitting here.
We can just go with demo program after.
Yeah, what's left in the slides? Oh, I just want to. Okay, so vision strategies. We should do that at some point. So you go to that spot to get the plugin, and then install it in Eclipse, and it tells you what to do. Like, it's got pictures of all the buttons you have to press and all that stuff. And then you'll have everything. You'll have all the tools on your laptop. Yeah.
So,
Yeah, I have my laptop over there.
if you want, we probably don't have time right now, but after we're done, you can come down and we can get you set up.
Oh, you should look at that those videos online. We'll show you the videos. Okay, watch the video, and it will go through writing the entire program from scratch. Okay, that's the best. That's the best you can do. We're going to talk about it here, but it's going to be a little fast, and so the videos you can start with.
So you can have your laptop. So there's a full video online, a full tutorial on grip, but all these are they're little wire connectors. So all you do is you click and you drag from one to another.
And we'll put it up, and you can see the URL.
And like, when you're doing the like fine contours, you
Yeah.
just like
Are any of the languages better
you
for
click
anything,
for it
or do
on
they
the
all do the
fine
same stuff? It's just more complicated?
Oh, how did I get fine
They all do the
contours
same
to
stuff,
pop
and
up?
they're just
So
different.
over here, this is the
So
operation
C++
palette. So
programmers
all the
can say that
operations
it's
are
not
over here. So I've done this a lot, so I know that I want to do
And
fine
that's
contours.
simpler.
But if you
But
don't
they
know,
have the
then
same
they're all listed here, and you can do all sorts of different things. So
People
if you
say
want to
that the
blur or
C++ stuff is
desaturate the
faster.
image, you can do
It may be
that.
a little bit faster, but it doesn't really matter.
So there's a bunch of
Writing robot
operations in
programs, so
here
I
that you
can
can
tell
use.
you that, like,
You can resize the image, you
like
can
the cheesy
save images to the
There's one of
disk,
these teams out in California that's like
all
a
sorts of
world-class
things.
team.
The best thing to do is to follow the tutorial because it'll talk about all of the common ones that that you want to use. But this is like the standard, like you just want to, this is like the short, simple, sweet version where this is like the bare minimum of what you need to get it working, where you give it an image, you give it a threshold, then you find the contours, you filter the contours, and then you send that data to network tables
Oh, yeah, these are the
so other
mechanisms.
people can use it.
They're pretty cool because you can make the robot go in any direction.
If you come
So
up
you can make it just
after,
go sideways, or
you can do
forwards or
more,
backwards, or 45-degree
in-depth,
angle.
and like if you
And in
have
fact, you can even
something
make
that
it
you're
spin
trying to
around,
find
and while
with
it's
the
spinning, it goes
we
straight
can
that
do an
way.
example for that.
So,
because I tried doing this last year, and
no. This is way small. The robots will build are like
RPG, and
80, 90, 100
it would
pounds.
see it,
or
but
something.
then when I was
This
trying
is
to
just so I can put it on a
make
table
it so it would just see that,
and
it
show
would
it. Okay, so
completely go haywire.
you know, and it has
So
like Vex motors.
something to
instead of
start out
real
with is
motors,
you really need good
you know, stuff like
images.
that.
Yeah.
So this image is like
a
a
demo
perfect image.
Now it's
And
actually
you get
good
this by lowering the
if you guys
contrast
want,
and
or you can afford
saturation
it,
on
or
the
you have
camera.
parts or something.
And then
It's
you
really
get something
good to
that
build
looks like
something
this,
like
and then
that.
it's really
Because
easy
then programmers
to
can play
go
with
from
it,
here
you
to
can
here.
learn about it.
This is
Because the
definitely
real
the hardest
robots
part,
drive at
though.
like
Is
20
going
per
from here,
second or
or
something.
the hardest part on the
And they'll
right
like,
side.
you know, they'll
is
like
going
run
from
over
here to here.
small children and cats. You know, and,
Part of that is
but
having
this
a really nice
is like
image
really
like this,
slow.
and part of
You
that
put it on a
is,
table, and you
I know what values
get your
work.
hand caught in it, like nothing serious.
Try
happens,
using an HSV though,
you know, and stuff like
and
that.
playing with it
So
because
this is like a really
it's
nice thing to
really
have.
it's really easy because with RGB you have to like think about the consequences of things. Where here, hue is
These are
just
not
the colors,
included,
so you
but
just
you can
kind of
buy
lower
these
it
from-
until
these are
the
little
target
baby
is
ones for the
visible
Vex robot.
barely,
But you
and
can
then you
buy
keep going
bigger ones
until
from
it's just visible. See
NVR
how it starts
and
to
from,
disappear.
and
So you go a
from
little bit
Vex.
more than when it starts
And
to
from Vex.
disappear.
So there's
And then
a-
same
go
thing with
to-
saturation. You just
Go to
bring
the Vex
this
website. and
bring
look
this
for
up
Vex
until the
Pro.
target doesn't start
That's
to disappear.
the FRC stuff.
So it's starting to
Pros.
disappear, so we're going to bring it
And they
back
have
down. And then this one, we're
bigger,
going to bring it
more
up.
rugged wheels
Started
that
to
are like
disappear,
this.
so we'll just leave it like
Now,
that. And then same thing with the value. You
The
bring this up
problem with
until
these is that
the target starts to
the
disappear.
way they work,
and then you
is the
bring
way
it
they
back
let you
so it's
move
not
in any
disappear.
direction is if you look
And
at the
then
wheels,
same thing over here.
the rollers
Just
on
bring
wheels
it down
point
until
like
it starts to
45
disappear up,
degrees.
start to disappear, bring it
And
back
this one
up
is
a little bit again.
45 degrees the other way.
And then what
And
you're
so by
left with is
changing the
you're
speed
left
of
with
these,
an
you
image
can
that
make
looks
it
like
move
this,
in
where
any
you have
direction,
your two
okay?
targets
Because the
and then a
force
bunch of
vector-
tiny
the force
ones.
vectors, they're this way.
And you use
and
the
that way.
filter
So if you
contours
change, if one
operation
of
to
them
get
goes
rid of
faster
the
than the other
tiny
one, it's going to slide
artifacts.
to the side. The downside of this, they're
Basically,
very maneuverable.
all I did was I
but
set a minimum area.
Because these are
So if the
pointing
area is
45
less than 100,
degrees
it'll
instead
throw
of
it
straight
away.
ahead, then the force and the speed has to be multiplied by
You can
some
take
of
a
those math
picture,
things.
or
The square root
can
of 2
send
over
this to
2.
you.
So it's like
Just file to you.
0.7. It's 7/10 of the pushing power and the speed of the same motors with conventional wheels. Okay, but conventional wheels don't go sideways. So if you got a game where you don't expect it to be getting pushed around and you don't expect to be having to go like uber fast,
2015.
and you want like maneuverability instead, if that's your deal, if you guys are looking at the game and you say our highest priority is to have a very maneuverable robot, more than a strong pushing robot or more than a fast robot, then these work great. Okay, but if you got that other stuff, then you got to consider that.
Good question.
What we found with this is that if the center of gravity is too
Yeah.
far off, then instead of moving sideways,
Yeah, there's two things about these that are kind of interesting. One of them is that the CG is off, which is really what causes the problem. The wheels have to turn precisely the measured amount, the calculated amount by the software, and if they don't, then it will not go straight or won't go the way you think it's going. And so on bigger robots, what people often do is they make the frame kind of flexible a little bit so that all four wheels are always on the ground. Because if one wheel's off the ground, it's going to mess up its motion.
both.
Okay,
power and
so
light.
sometimes teams
So
have
how
chassis
is
that kind of like
their
the
complex,
front and the back
like
are
very
tied
complex
together with a
machining
pin in the
process,
middle,
or they're
and they can do
3D
this.
molded?
So they can ride over uneven
Yeah, most-
things in
most
the
people buy
carpet
them like
and stuff
that.
like that, and it still works.
And why is
So you
you
have to
can
be really
move in any
careful about
direction.
that if you're using these.
So here, I
these,
actually have a,
wheels
like a little,
that,
I have a
that
demo.
all four wheels are in contact
See.
at the same time, or you won't be able to get the thing to drive in a straight line autonomously.
Yeah, most FRC frames are flexible.
Yeah, and often they're flexible enough,
Yeah.
and so so that might work. So these are fun to play with, and they do really cool tricks. You know, because and
If I can
actually,
find
if you use a gyro sensor, so you can know which way the robot is pointed, then you can do what's called field-oriented driving, which is really adding a few lines of code to your program. If you use the WPILib software that does the driving stuff, which means that you push the joystick forward, the robot will go forward no matter which way it's facing. So if the robot is just like this, and I'm here, and I push it forward, it will just go this way without changing its orientation. And then they use the rudder control on the joystick to make it rotate. So if you want it to rotate, so if you want it to move in some direction, the direction vector comes from which way you do the joystick, and the rotation comes from how you twist the joystick.
Here, so
So you can make it go straight. Oh yeah, here. Yeah, so you can make the robot go in a straight line. Where'd that come from?
a team made it.
Oh, yeah, so you can make the robot go sideways. You see what happens? These vectors are bigger, and it goes sideways. Okay, and that kind of shows how it works. So you can make it go any way you want, and that makes it rotate. And so you can make it rotate and move at the same time. Okay, and try that with wheels. You know, and so it's very, very maneuverable. And so they use it for like forklifts in tight spaces, because the forklift operator goes down an aisle, grabs the stuff, just backs up a little bit, and then just goes this way. Okay, because they can't make the turn because the thing they pulled out, you know, like the lumber they pulled out of the thing is wider than the aisle, you know, and it can't make the turn. So they just go out sideways. Yeah, here's template. Oh, that's pretty nice. Oh, you'll have to tell me where that is sometime. So, sea monsters. Yes, that shows how it works. Okay.
Can I show an example of the code?
The code is actually pretty easy. I think we have sample code online.
For Mechanism Drive?
Yeah.
Yeah, so it's really easy.
You'll see it.
We'll see it. Yeah.
It's built in. So you can say you want to drive this with tank drive. You can use a class where you say drive this with tank drive, but with the same class, with the same everything, you can say, oh, I really want to drive with mechanism drive, and then you give it a rotation value and a direction vector, and it just does it. Okay, hey, let's get going. But leave this up. This is cool. Wait. A lot of you guys were very interested in the wheels on this robot. The mechanism wheels or mechanism wheels. I'm not sure what the guy's name is. Hey, guys?
So you guys, this robot has really cool wheels. And what they're called mechanism wheels. And what it lets you do is it lets you move in any direction. And there's a little demo here that demonstrates that. If Brad wants to explain a little more.
So the wheels, if you come up and look at the wheels later, you'll see that there's rollers that went 45 degrees in on the front, 45 degrees in on the back. And so that means that the direction of the robot, if all the wheels are going the same way, then it drives forward. But if the wheels are going in different directions, and you can see these direction vectors for this, that represent the speed of the wheels. If you make the different wheels go at different speeds, you can make the robot go in any direction you want, and without turning. So it's like really neat. This rotate too.
Yeah.
Okay. So you can rotate and move. I don't know if this does it, but you can be rotating and moving at the same time. With the joystick, it's pretty sweet. Using these things. So so you can stray, do all that stuff. So, but what we were saying before was, just so you know, the upside is you can do these like beautiful maneuvers and you just like driving that people won't believe that you're doing. The downside is that since the rollers on the wheels are pointing 45 degrees, if you do that trig stuff, you'll find that the speed is reduced by the square root of 2 over 2, which is like 0.707. So the speed is reduced by 0.707. This is the 45-degree angle, it's the triangle, and the pushing power is reduced by the square root of 2 over 2. So if you have a game which favors maneuverability over pushing and speed, these are great. If you have a game where pushing is important or going as fast as you possibly can is important, then having conventional wheels gets rid of that that 7/10 loss, or 3/10 loss. Okay, in pushing power and speed. So it's just one of the decisions you have to make when you look at the game and the team is brainstorming and figuring out what to do. If you want to use these, it's great, but only if the game favors maneuverability above everything else. Otherwise, you're much better off with the other wheels. The normal, straight, pulsing rubber wheels. Okay, this is where we are right now with all this stuff. Oh no, we're actually up here somewhere. Okay, first, so a lot of you guys are asking about where the code runs, and we said, wait a second, we'll tell you later. So here, this is later, and so there's 3 ways of doing this, basically, or maybe there's more, but there's at least 3 ways of doing it. Put the camera, plug the camera into the USB port on your RobotRio, and you run the vision code and the robot program on the RobotRio. So some people have reported that when you run the vision code, which is often compute intensive on the RobotRio, then the vision code either gets interrupted by the robot or the robot gets interrupted by the vision code. And if you're not really careful as the way to program it, then you may have trouble getting all that stuff to work at the same time. The second way of doing it is you plug the camera into the RobotRio, and then you send a video stream from the camera to the laptop, and the laptop, all these Intel processors and AMD processors have special instructions that make vision processing go faster, among other things. And so you run grip or you run some vision program on your laptop and just send back the numbers. Those numbers you saw at the end of the pipeline, which is like, where the targets are. So you're sending back a whole image, but you're returning to the robot with, a dozen numbers, which is really fast. So the other way of doing it is to run it on the laptop. And the third way of doing it, which is getting really popular these days, is people get like a cheap computer, like a Raspberry Pi, which you can buy for like $35, and they run OpenCV and network tables on here, and you put your vision program on here, plug the camera into here, so you're not bogging the RobotRio down with anything, and all the vision stuff just happens on the Raspberry Pi, and then over Ethernet, it sends those numbers to the robot. Okay, so there's 3 choices. This is probably the most complicated of the 3 choices to get working, because you got now 2 computers in the mix. You got to kind of sort out. The easiest thing is just to send the stuff back to the laptop and run grip or something. And the other thing you can do is you can run grip, generate code, and put the Java program, the generated Java or C++ program onto your RobotRio and just run the code back. So those are the choices. Yes?
Are there instructions for setting up network tables to run on the
There are.
So there's even better. There's a sample project already set up for you. So all you have to do is download the sample project. It is called, hang on, I don't want to mess up the name. It's Vision Sample or something. Hang on. Vision Build Samples.
Okay, so GitHub. Okay, so all of this stuff. See how it says, this is GitHub. And here, scroll again. See how it says WPILib suite / Vision, it's Vision Build Samples. So for each of the repositories, for each of the tools that we have as part of all the stuff that you get, it will be under WPILib suite. So if you go there first, here, just click on WPILib suite. Here's all the tools. There's this stuff. Here's WPILib, the camera server, the network table stuff, shuffleboard, smart dashboard, some utility libraries. And if you scroll down, there's like a ton more. So all this stuff, these are all the things that get built together and packaged to make your distribution when you install an Eclipse. So it's pretty complicated, but it's all right there.
All of the instructions are right in this file. So all you have to do is download this project to the Raspberry Pi and follow these instructions. It'll walk you through it, and then you're good to go.
Yeah, and I think Thad or somebody was making well, I think one of the guys was making a Raspberry Pi image. So you could just copy the image onto your Raspberry Pi with network tables and everything, and OpenCV and everything installed on it. And now all I got to do is write a Python program or something to do the camera stuff. Okay. What was left? So that's the 3 ways that people use this stuff. You can, and you can, if you have a RoboRio, you can play with all this stuff right now. If you don't have a RoboRio, you can play with Grip or something, or writing programs on a laptop right now. You know, or you can get a Raspberry Pi and put stuff on there and play with it right now. You know, plug out a USB, you know, like a $30 USB camera into the Raspberry Pi and play with it. Okay. Oh, we have online curriculum. This is like really cool. Like 4 years ago, I convinced the school to pay some students for a summer to make a bunch of videos on robot programming. And those are, can we find them easily?
There's a link on the screen steps to them.
So they're
Everything is through screen steps. If you're ever looking for something.
So there's a bunch of videos that will like get you started.
Oh, oh. Yeah, there's a link for it here.
Okay, so if you go, this is one of them, but if you go up a little bit, you can see a bunch of playlists. Do the playlists. Okay, so here's oh, forget that. That's if you come to WPI and you want to know about introductions to labs, you can go here. You know, for the labs, you take the introduction to robotics course. But this is using here's control stuff. It explains about PID loops and all that stuff. It's one of the WPI robotics faculty members. This is how to use RobotBuilder. This is using don't do the gazebo stuff. This is all about motors. There's 5 videos. These are outstanding. They explain. A lot of people don't know this, but there's curves for the motors, and you can get predictable performance from the motors, and you can operate the motors at their most efficient range of power by using these graphs. And so if you go look at motors, this is Ken Stafford. He will explain how this works, and I'll go through some examples of getting stuff to work so you can see it. There's Ken right now. This is the intro video, but then the next one. So here's the video. So if you look at it, he's kind of explaining about motors, and it's kind of nice. We did like really cool animated graphics for the video, so you can see things. So we spent a lot of time doing this. And here, go back to the list of playlists. So that's motors. This is about it says signal type. It's sensors. I don't know why it says signal type. This is about sensors, and there's a whole bunch of sensor videos here. So rotary sensors, signal types, range sensors, serial communications, all this stuff is explained, in ways which works for either WPI freshmen or high school students. There's like no math, any of this stuff, or no complicated math. This is Ken again talking about pneumatics. This thing is great. This is a really, really good video. You should watch this. In fact, it was actually really funny because sometime one day during the build season, I got this phone call from somebody, and it turned out it was like a mentor for some team that was like in South America or something. I don't know, somewhere like really, or no, it was like New Orleans. And he said, I was watching this video about pneumatics, and I want to see if you can help me and answer some more questions about pneumatics. And I said, well, I can answer a little bit of stuff about pneumatics, but I can get Ken Stafford, who is sitting in the office next to me, who can really help you with pneumatics. And he said, wait, do you mean Ken Stafford from the video? Was it that Ken Stafford? And I said, yeah. And he said, oh, that's amazing. And he said he was talking to the person who was in the video. He's like, it was like a rock star thing or something. It's like, so that's really good. So he talks about all this pneumatic stuff. And you can play them at different speeds, so you can play faster if you're bored. And it goes through all the pneumatic stuff. And what else was there?
That was it.
So the ones about RobotBuilder.
RobotBuilder.
The ones about RobotBuilder, there's one of these things that, here. This is an overview of RobotBuilder. Here's how you define the robot subsystems. Here's how you do the test mode stuff we talked about. Here's how you create simple commands. Here's how you make advanced commands. Here's how you write commands for driving the robot. Here's how you connect commands to the operator interface. This is the thing where you watch these videos, they're all like 10 or 12 minutes apiece, and you will see everything about programming this robot. Okay, so that's like pretty good. Okay. Or the mystery of the pyramids construction. I don't know what that is. Okay. So yeah, so check this stuff out. These are really good. Not just for programming, but for those other things also. They'll really, it's really good for like freshmen, come onto your team for the first time. Get them up to speed. They can look at the videos, and they're pretty interesting. Current status. So we've been in beta for a couple of weeks. So that means there's 90 beta teams approximately, which are testing all this stuff. So there's 30 teams testing Java, 30 teams testing C++, 30 teams testing LabVIEW. If you guys aren't, no one here is a beta team, right? If you want to be a beta team next year, when they put out the call for beta teams, you can sign up for it. You can get the software early and start playing with it. So that's kind of nice. There's the Open JDK, the new Java that we were talking about, is now up and running on the RoboRio. Shuffleboard is not quite feature complete, but it's getting there. And most of the changes which we talked about before are in there and running. So that's pretty good. Is that the end?
Yep, that's it.
Okay, cool. So you want to do the program?
Yeah, sure.
Should we do that now?
So as mentioned, RobotBuilder has a little bit of trouble right now. Not because of us, because of other libraries that we're using that need to be updated. But we'll just show the RobotBuilder program that we made earlier, or last night, in the middle of the night. So we have our different subsystems here. So we have a claw elevator. Well, we have a drive base, which is the wheels. We have a claw, which will open and close the claw. So if you wanted to grab something with this, we usually do a soda bottle. You can. A wrist, which will move the wrist up and down. And of course, the elevator, which moves the entire thing up and down. And all you need to do is, after you create the subsystems, drive base is special because you have to connect all 4 motors together into something called a robot drive, which lets you do arcade drive and tank drive and mechanism drive. But once you do that, all you have to do is drag your motor controllers into the subsystem, and it will add them to the subsystem, and then you're able to control those motors and actuators using sensors, either using PID control or timers, which we have examples of both. So for example, the claw, we're going to use a timer for because we don't have a sensor on the claw. So the way we programmed it is it'll just run the motor for 1 second to open it, and then it'll run the motor for 1 second to close it. I don't recommend that on your actual robots. Use sensors if you can, like use a limit switch to know when you're open, to know when you're closed. But for a little demo, this works fine.
Yeah, these are like baby motors. You take the motors that come in the kit, and you just run them until the claw things mash together. And
yeah, the whole thing will fall apart.
You see a lot of smoke, and then you have to buy the motor.
Yeah, these motors are not strong at all. Yes? Mm-hmm. Maybe. There are other problems you'd have to solve because the totes were really heavy that year. So if you did something like this, your center of gravity might go in front of your forward wheels, and then your whole robot would tip over, and that's not fun when your robot's tipped over. So there's other problems you had to solve. What teams did that year is they would put the arm at the back of their robot, and the totes would come into their robot. So the center of gravity was always between.
So
I forget the word for it.
The robot was shaped like a U, and they pulled the totes inside, and they just lifted them straight up. So the totes were lifting at the center of gravity of the robot, so it wasn't tipping. And so they would lift them up and then drive to another one and lift that one, lift up to 2, and then drive to another one, lift up 3. So you make these stacks of totes. But if you have them way, like Austin's saying, if you take a laptop or something and hold it in your hand like way out here, pretty soon your arm's gonna be hurting, and then soon after that, the laptop's gonna be on the floor. So you don't want stuff to be like way outside of the center of gravity of the robot.
But that's a mechanical issue.
It's fixed with software.
Can't really fix that with software. And then the elevator and the wrist, they're PID subsystems. So we're not doing the 1 second thing. We have potentiometers, which will tell us exactly where the the mechanisms are in their range of travel. And then we can say, using a PID loop, which is proportional integral derivative, to go to that loop, to go to whatever set point we want, which is where we want to go. So
Wait, before you go, who does not know what a potentiometer is?
oh, okay. So do you want?
Okay, sure.
Okay.
So potentiometer is, like on a stereo, there's like a volume control, and you turn this one knob. And
Who knows what a stereo is?
So well, times have changed. They don't use potentiometers anymore, but they did. And what it is a variable resistor. So you turn the thing, and this little thing turns around a little track of carbon that changes the resistance, through the little carbon trace. And so you can measure the voltage from the potentiometer, and as the resistance goes up, the voltage goes down, or something, and then you can take that voltage and you can, it's proportional to the angle of the knob on the volume control. And if you connect the knob to the wrist joint like this, so that the potentiometer is here, then it measures this angle, and then you can write code that drives until it gets to the right angle. And so that's how you use a potentiometer for that.
After we're done, it's really hard to see because the potentiometer is inside the wrist, but you can come on down and I'll point at the potentiometer. It's just a little mechanism, and they sell them on Andy Mark, and you get a couple in the kit of parts too. So
the other thing you use to measure angle or measure wheel rotations or something is called an encoder. And like on your stereos, the problem with potentiometers is that after you use them for a long, long time, the little carbon thing gets a little dirty and it starts, it starts getting noisy when you turn it and stuff. You probably heard that, where you turn the volume control on an old stereo and it's kind of scratchy sounding as you adjust the volume. So what they do now is they don't have volume control. The volume controls aren't potentiometers; they're encoders. And as you turn the wheel, there's a little disc with a bunch of slots cut in it, and there's a light shining through the slots and a photocell on the other side, and it counts how many slots went by. Okay, and that thing is not dependent on getting dirty or any of that kind of. Well, if it gets dirty, it's bad, but they're encased in a package, so dirt doesn't get in them, and so they just work.
But there are problems to solve with that because they're incremental rather than absolute. So with a pot, you always know where you are in the range of travel. But with an encoder, if you lose power, you don't know where you are anymore. You have to find some way to figure out where you are, usually using a limit switch or something.
So those are the kind of rotary sensors. If you look at those videos and you look at the two things about rotary sensors, like digital and analog rotary sensors, it explains the whole thing in gory detail. So that's a good place to look at that.
So yeah, those are the two different kinds of subsystems we have. We also have a couple of commands here before I gave up and started. What?
What you said that the elevator and the wrist were what kind of subsystems?
PID subsystems.
Who does not know what PID means?
We kept skipping. Okay, so PID stands for proportional, integral, and derivative. And all those are different algorithms that can be applied. So all you do is you give it an input and it gives you an output. When you get to more advanced math, you'll learn what a derivative and an integral is. But for right now, all you have to know is that an integral is the area under a curve and the derivative is the slope of the curve. So if you're giving this PID controller some input, it's able to calculate the short-term integral and the instantaneous derivative of the input, and then using some constants, you convert that into a motor output. There's ways of doing PID control without knowing how it works. The common method of doing it is you just keep raising the p-value up until your mechanism starts to wiggle. And then once you have that, you just lower it back down, and then you're pretty close to good. And that's actually what we do here, is we're only using proportional. And what that means is for some sensor error, we're giving the motor some output. So when we're 10 centimeters away, we're giving it full power. And when we're 5 centimeters away, we're giving it half power. And when we're right on target, we're giving it nothing.
You could say that the speed of the motor is proportional to the error, which is why it's called proportional control.
And then integral it takes the integral of the error, so it keeps adding up the little errors. So if you're, what happens is if your P is too low, your set point will be slightly higher than where you are, but the motor won't be getting enough power to overcome friction or gravity or whatever to get to your set point. So what the integral does is it lets you get to your set point after a certain amount of time, after it adds up the little errors to get to something where the motor can start moving again. But you have to remember to get rid of that afterwards, or else it'll just keep adding up until you go way past your set point. And then you're like off the rails and your robot's falling apart.
You can find lots of examples of this.
Yes.
Yeah, just keep going.
Okay. That's PID. P is great though. If you're only using P, you're like 95% of the way there, and your robot will mostly do what you want it to do. And then I and D you can mess with a little bit and watch the videos and learn more about them. That's PID. So we have time or some other method and PID control.
Why did you use PID?
Because I have sensors on the mechanisms. So you want to use PID because it's really annoying for your drivers to have to sit there and be like, okay, it's at the right height right now. Oh, my finger slipped and now we're no longer at the right height. It's much easier to just have a button that says, oh, go to the bottom position, and PID will take care of it.
That's why you use it, because you wanted to go to a specific position.
Yep.
Yeah, and the position is called the set point.
Yeah.
Yeah.
Yep.
The position is called the set point, and all these control. So you could just say drive the motor till we're at the set point, but then what happens is it's like inertia, and the thing drives way past the set point, and then you're like, and you miss it, or or something. And so what all this control stuff does is it's an algorithm for letting you drive it right to the set point and stopping and holding it there. And so that's what this is. And that stuff, that PID stuff that Austin was talking about, that's these numbers here. And you can just type in the numbers and it will use them. And if you look at the video, it explains where the numbers came from.
Okay, those are the two kinds of subsystems. We have some commands down here, but because we're in beta and I'm kind of mixing and matching different versions of the software, I gave up after writing 3 commands because it was too annoying to use right now. For you guys, it won't be annoying to use. You just run it, and all you do is once you have everything set, you can come up here and click your language. So you can click C++ or you can click Java, and it'll generate the code for you and put it into an Eclipse project. And all you have to do in Eclipse is open the project. If you make changes in Eclipse, you can still make changes in RobotBuilder, hit the button again, it'll save all your code as long as you don't put it in the 2 special auto-generated comment blocks. The other cool thing that RobotBuilder does is if you put everything in and you don't change the port numbers in Eclipse, you can hit this wiring table button and it'll generate this wiring table for you. So if you go to a competition and I don't know, your robot catches fire or something, you don't have to change any of the code while you're rewiring your robot. You just have your wiring diagram here, and you hand it to your wiring guys and say, this is where everything's plugged in, plug it back in. So it's really useful to have at competitions. Even if you don't use RobotBuilder, this is something really useful to have at competitions, which is, this is where this is getting plugged in.
How did it come up with that?
So I gave it the port numbers earlier.
Yeah, so when you add a speed controller, you give the port number.
Yeah.
Okay, and so it just takes all the port numbers for all the sensors and for all the speed controllers. It makes this wiring diagram. So you could before, when you're designing the robot, before anybody's wired it or anything, you can write all this code and make all these subsystems and just choose ports, arbitrarily. Say, oh, this plugged into port 5, this plugged into port 6. It really doesn't matter until somebody wires it. And then you just print this thing, and when the robot's finished and it's ready to be wired, you hand them the wiring diagram and say, make it like this, and then it will work with my program. Okay, and that's like really nice. Otherwise, they just pick things randomly and plug them in, and then they tell you where they are, and it doesn't match your program, and you got to go back and fix everything. So
that could be PWM.
Yeah, PWMs.
It's for any port, CAN IDs, PWM ports, analog inputs, digital outputs, digital inputs.
Yeah, click on one of the challenge.
So there's a Talon. In this case, it has the CAN ID because all the CAN speed controllers have an ID number. And on ours, if you look at it, and you should do this too, we put a piece of tape on top of all the speed controllers with a big number on it that says what the ID is. And then you, once it's all built, you run some software. You can program the motor controllers with the correct ID number, and then your software will work.
When you hit the Java button, it'll generate this program for you. And ours is a little bit more filled out because I was working on it last night. This is your robot program. And what you can do with it, without writing any code, and well, just trust me, I didn't write any code to change this, is if you run the program in test mode, it'll populate the smart dashboard with little sliders you can use. So here we can do that right now.
Is it still, is the battery dead yet or something? Does it still go on?
Yes, the battery is very dead.
Okay. We'll get another
One moment while we change batteries.
Okay.
Do you guys have an easy way to do the CAN IDs? We just like end up going like one at a time.
So the easiest way that I found to do the CAN IDs is, is just one at a time in the web interface. And you can use the cross-the-road lifeboat software to do it, but if you're not on Windows, you can't use that. So one at a time in the web software. If you have multiple plugged in, like straight out of the box plugged in, you can change them like one at a time. It'll figure out like, oh, only send this new ID to one of the 10 zero talents. So what I do is I'll say, oh, assign that one to be number 30. And then I'll go through, get rid of all the zero talents, and then go back through again and reassign all the numbers that I just assigned to the ones that I actually want. So I'll say, oh, you're going to be Talon 1, you're going to be Talon 2, you're going to be Talon 3, you're going to be Talon 4.
It flashes the lights on the Talon that it's selected so you can see which one you're programming. So you know whether it's, the left front or the right rear, or, that kind of stuff. So.
Okay, so I'll just enable test mode.
Oh, it's not up yet. Any questions during this brief 40-second introduction?
Start playing Cotton Eye Joe.
Yeah, if you have a Mac, you're a Mac user. I'm a Mac user. Congratulations. If you have a Mac, there's two ways of running the software on it. One way is you can run Parallels. Okay. Well, one is you can dual boot it. So you have Windows and Mac. But then the problem is that if you've been developing the software using Mac OS and then you flip to Windows and you lost all the development tools. What you could do instead is if you get Parallels, which you can get like the academic price for Parallels, like $35 or something like that. Then you can install Windows on the Mac, and so you can have both running side by side.
Yeah, that's what I'm doing.
So this is Parallels. See, it's a full Windows thing, just on one of the screens on the Mac. Okay, you can install whatever you want on it. So you can install the imaging tool, and you can install the all the stuff.
I have the driver station. I have the FMS. I have SolidWorks, the VPN, bunch of stuff.
And you don't have to reboot. So that's like a really good. That's like the best way of doing it. The other thing.
But don't do that on the field.
Don't show up with the.
Don't show up with Parallels on the fields. The FTA will get really upset with you, and then hand you the loaner laptop.
Yeah, I mean, if you show us something weird, nobody will be able to help you. And so make sure you're running standard stuff when you go to a competition. Yeah, so that's sort of the way of doing it. The other thing you can try, if you want, is this thing called Q Driver Station, which you can find online if you search for it. And it's a driver station which is cross-platform, and it will run on Macs. But it doesn't have all the features of the real driver station, because the real driver station is like a really hard program to write and get right. So, but Q Driver Station will let you enable the robot and disable it and set the codes and stuff. And it runs on Linux or Macs.
Okay, so I'll just do it again. I enabled test mode on the robot, and without writing any code except using the RobotBuilder code, we get this, which is we get the elevator subsystem and the wrist subsystem and the claw all on the dashboard. What you can do is it has these nice sliders, so you can drag the sliders around and the robot will move without writing any code. And this code is always available to you. So if your operator comes and says the claw was broken, you can then just slide the claw here, and when the claw doesn't move, you know that it's not a programming issue because we test this stuff very heavily, although it could be the wrong port number. But your complex code, it wouldn't be the problem at that point, and you could move on to trying to figure out what the real problem is. The other thing this lets you do is it lets you tune PID. So on the elevator, for example, here, I'll just test it using the slider real quick. We can move it down and move it up using the slider. It takes a little bit more. If we enable PID on the elevator, if we give it a set point and enable it, it'll just go to that set point. So for example, I happen to know that 0.3 volts is the low position on the elevator. So if I type that into the set point and then enable the PID controller, give it some correct inputs there, it'll just go to the bottom. And then if I run it again with 0.6, which I happen to know is the top, it'll go up to the top and then stop, which is great for testing PID.
Then you copy these PID values into your program, and then the program works just like it did in test mode.
And then this also works for the wrist. So if we set the wrist to 0.85 is the up position on the wrist, it'll go up. And then if we set the wrist to be 0.7, it will go back to horizontal. Okay. I leave the robot enabled. Don't hit enter if you're programming, because the driver station, when you hit enter, it disables the robot. And if you hit spacebar, it's e-stop. So if we try that again, it'll go back to horizontal. So yeah,
the key is it's going to predictable positions, and so you can set that up in advance because you know how high all the scoring things are in the field. So you can just write the program so it goes up to the right height, and then when you get there, it works, and you don't have to mess around with it. And
so what you saw there was the PID loop is not tuned right now, so it's going to jitter a little bit.
Oh, the other thing I was going to say is if we move this up by hand, which I can't do because it's disabled. If you move this up by hand and you watch, which one is it? It's,
this one right here.
There, there's the potentiometer value, and you can see how it's changing as it goes up and down. So that's how you can find the set points, just by moving the thing up and down, and that's the analog value. So that's the input to the PID, and the output is the motor speed. Okay, so this lets you see all of that stuff right here, and then you can tune get the robot all tuned and working. Okay. Yes. No, the potentiometer, like Austin said, the potentiometer is just the position of this little arm on this carbon thing inside there, the position of the volume control. So those are absolute. So every time you reboot the robot, it comes back with the same value. So if we were to not touch it, turn it off and turn it back on again, it would still say 6.2 or 0.62.
Oh, those buttons are broken. I can't do it. The driver station buttons are broken.
I said turn off the robot, go to sleep, come back the next morning, turn it on. These values will still be the same as long as nothing's moved. Okay, that's the advantage of potentiometers.
If you're using an encoder, it doesn't work like that. An encoder, you have to, when the robot turns on, re-zero it in some fashion.
Right, every time you turn it on, it's 0, and it doesn't matter what position this thing was in. It's saying, oh, 0, because it's counting how many of those little slots go by. And there are some absolute encoders which effectively work like potentiometers, like expensive potentiometers. Yeah.
But you have to go past the 0 position on them still to re-zero yourself. So they're absolute, but if you reboot, you still have to go through the travel range in order to find the indexing pin on the encoder.
There are some that do.
Oh, okay.
Yeah,
So there are two. There are encoders with an indexing pin, which will let you index on it, and then there are absolute encoders, which are less common, which also let you do that, which have individual digital values for each.
Yeah, so watch the video. A lot of that stuff's explained. And then the other thing you can do is, if you're interested in encoders, look at what's it called? Digital. What's this? Who makes the encoders?
US Digital.
US Digital. Look at US Digital, and they explain all of this stuff about how all this works and different models of encoders. You know, like what the maximum speed is that an encoder can spin before it doesn't work anymore. You know, and stuff like that.
And then just to demonstrate, we so after you write some code, you get these buttons automatically, but they don't do anything at first. After you write some code, you can get all these commands to do things, and for every command, you get a button on the dashboard. And all you have to do to test a command is hit start, and it'll run it. So that's like the start, the claw open command. We have claw close command, and for all of them, it just works. Now, what those commands look like is here. We'll look at the claw open command. The claw open command is a timed command, and this is really useful if you're just doing something off of time, because all you do is in the constructor you tell it how long you want it to run for, and then after that time's up, it'll be done. So we can look at it. So while the command is running, it's going to tell the motor to run at the open speed, and then when the command is done, it'll tell the motor to stop. And that's all this command is. And we can look at the open and close methods. All they're doing is they're setting the motor to a speed. So we're just setting a motor to a speed for a certain amount of time and then telling it to turn off. And that's all it takes to do timing.
So this is the subsystem where you put the stuff in there that actually drives the motors and stuff on the subsystem. And the command is the thing that does all the timing and all the interactions to make the thing happen in a way that you want it to. So subsystem here, command is like the claw open thing over here. And this is calling methods on the subsystem. Okay.
Now there's this cool thing called requires here, which means you can only have one command running on a subsystem at a time. So you won't run into the weird issue where one subsystem is telling the claw to open and one command is telling the claw to open and one command is telling tell the claw to close at the same time, because what happens when you do that is the claw will just sit there and jitter because it'll be set to open the open power one loop and then set to the close power in the same loop but a little bit further along in that loop. And it'll just sit there and shake. So this prevents that. If you don't put this, then none of the motors will, like you won't get that safety built in. So definitely use that. If we look at the PID commands, so for example, the wrist command, this one's a little bit different because instead of giving it a time, you give it a set point. And all we do in the command is we save the set point, we use this special requires thing again. And when the command starts, we enable the PID controller, which tells it to start processing the input, and we tell it what set point we want it to move to. And it'll just keep going until this isFinished method returns true. And if we look at the isFinished method, all it does is when the robot wrist is on target, which means the error is small enough, it's within a tolerance that we specify, it'll stop. It'll return true, the isFinished will turn true, and then the command will stop and release the subsystem so somebody else can use it.
Oh, and by the way, for PID commands, stuff is all completely written by RobotBuilder.
Yeah, we didn't write anything for this. Only for the claw did we have to go and write methods. Yeah, the one sentence, the one line of code that told the motor to go at the correct speed. And then the little helpful thing I did up here, which RobotBuilder did not generate, was I added constants for what the set points for the wrist are in the command. So if I wanted to use the wrist command, I would just do like new wrist command and then wrist command.up. So I don't have to remember what the number was for the set point.
Show one of the groups.
So this is the autonomous program for this robot, which will drive forward, pick up the can, lift the can up, and stick it on a box, and then drive away. And all we're doing is we add So the way it works is you add parallel commands and then you add a sequential command. And every time you add a sequential command, it'll execute all of the parallel commands and itself before it at the same time. So this robot has a couple different steps that it goes through, but it can do many different things in each of those steps. So in the first step, it's setting the elevator to go down, it's opening the claw, and it's putting the wrist horizontal. And then the next step it does is this says drive reverse, but it's actually forward on this robot. You can switch that doing just adding a negative somewhere. And then the next step that it does is it closes the claw. Oh, we have another parallel, so we're not going to run this command immediately, but we're going to add it into a group of commands that run at the same time. We're going to lift the soda can and the elevator up, and we're also going to move the wrist to the up position. And then once that's done, we're going to drive forward some more, and then open the claw and drive reverse. So place the soda can and back away.
The whole thing with the serial, I mean, the sequential and parallel things, is that in this case, once you close the claw, then you can move the elevator and you won't drop the soda, or you can move the wrist at the same time. So you might as well do them both at the same time because it's faster. And so it does the elevator command up in parallel and does the wrist command sequentially. So it gets them both going at the same time. So while the elevator's going up, the wrist is moving. So it's going like that. And so it goes more quickly.
And we can see all of those run if I run the auto command and hold my hand so it doesn't fall off of the box. It picks up the can, drives forward, and then places the can and then backs away. Now, obviously, none of that will really work because it's so short, the driving distances are wrong. But with a little bit of messing with the numbers, that's your basic autonomous program. And that would even work for this past year's game with the gears, right? You just pick the gear up, drive forward, put it on the peg, release, and then back away. And suddenly you've scored a gear in writing not that much code.
Yes.
Yeah. Yeah.
Oh, this is? Yeah,
Yeah.
This is just like your competition program. It is simple. Oh, yeah, that's what we were saying
That's the point.
At that first slide, we're saying, you know, if you do this, it's going to be a lot easier. And this is the easier. You're seeing it now.
Yeah.
Why would you not use this?
So when you've been doing this for a very long time and you want to do really complex things, like do a like steady state machine, which are like fancy control loops for setting speeds on things, then maybe it's easier to roll with your own thing and not use this. But other than that, if you're not one of those teams that's like doing crazy stuff and like really crazy stuff that we don't have examples for online, then maybe it's a good idea to consider not using this. But if you look at all the teams that don't use, all of the teams that are doing that, all of their stuff kind of looks like this. It's just written slightly differently so they can control certain timings for their application better. But other than that, if you're new or not doing crazy stuff, you should definitely do this and not do something else or something silly like using Sample Robot or something like that. That's the biggest mistake we see, is not using this and instead trying to roll your own stuff too early.
Yeah, I mean, so the whole idea was that when we designed this, we said, what would be like a really easy way to write robot programs? And we had this vision in our heads when we started. And then over the years, we implemented it so that you could write this program this way. Because we thought way back in the beginning, we said, this is the best way to write a robot program for somebody who doesn't have a lot of experience. And now it's kind of fleshed out and all the tools are there. And so you can do what we're showing. Yes?
We have the really competitive teams. If you watch the videos, they talk about motion profiling.
Yep. Yep.
Can you do that stuff?
Yep.
Okay.
So all you have to do motion profiling is you have to, in your you have to add all of the motion profiling stuff out. Like obviously you need the code to do that. And then after you do that, all you do is all of the motion profiling libraries have a like motion profile.execute method. And all that does is you give it the motors and you say go, and it'll run a step of the motion profile. So all you do is you put that, like run that step code in a command for the drivetrain.
In the execute method.
In the execute method, and it'll just go and it'll run it. The people who produce the libraries for that have examples, and if not, you can always like there are different forms, like the first forms where you can ask for help, and people monitor those all the time, and they're happy to help get you set up with that. The other thing you can do is if you're running CAN talons, you don't actually need any fancy libraries. You just tell the CAN talon, run this motion profile, and it'll just do it, which runs way better than running your own thing, unless you have to do something crazy where you have to do like collision detection or link multiple motor controllers together. That's the best way of doing it, because the CAN talon can run the control loop so much faster than the RoboRio can.
But the Crustor Electronics guys actually are trying to make it so you can have a whole drive base and supply one motion profile for the whole robot to move in a particular way. And so they're trying to get that stuff working for this year. So yeah. They're working. I mean, they're doing it right now. They've actually, if you go back and you look at it, you'll find, fortunately or unfortunately, that all the Crustor libraries have changed, and the code's not compatible. Even the names of the classes have changed, so it's really not compatible. Huh?
That's terrible.
Yeah.
You can't load the old code.
Yeah.
We know.
Yes.
Yes, we know. We're aware.
What we did was a couple of years ago, we unbundled the vendor libraries from our stuff, because we wanted them to be able to operate at their own rate and not be forced to release their stuff in time with our releases. And so they found some bad bug, they can put out a new release like the next day, but our release may not be for another 2 weeks. And so we wanted to be able to separate that. And so it's much better for them, but at the same time, like the problems that Austin was talking about that made it so we couldn't keep using RobotBuilder was because they were a little bit behind where we were, and the CAN talon libraries didn't work with RobotBuilder. And so we sent them a couple of email messages, and they'll fix it. It'll be fixed next week, but it didn't work at this minute. So any other questions? We're actually getting kind of close to the end of the time. In fact, I think we're past the end of the time.
Yeah.
Do you have questions about anything? No?
If you do, you can come down after.
Yeah, we'll be around.
We're around till 2, which is when the car parking meter expires.
Okay, and this is not a PID value or a time. This is the room where you can get lunch. Okay, 2:15. So if you guys want to grab some pizza, you can do that. And like Austin said, we'll be floating around somewhere. And feel free to keep harassing us until 2 o'clock when they lock the garage.
Do you want to leave it on so we can demo, or you?
Oh, we could. We could.
Let's just leave it for now.
All right, I'll plug it in. And leave it till the battery
Thank you.
runs out. You're welcome.
Thank you. Probably cost money.
Yeah.
Yeah.
I'm still a bit confused on how it's used. Is it the red thing right here? No.
So the potentiometer is the red thing right here. It's contained in that housing.
Yeah.
What PID does is this sensor returns a voltage between 0 volts and 5 volts.
Yeah, so
And what we do with that is we say, oh, if we get a value from the sensor of like half a volt, that means that we want to run the motor at a certain power. So that's the P of PID. It's just saying when we have this value, we're going to run the motor at this value. So So what you end up with when you just do proportional,
scroll down.
Because you're like X, Y.
Yeah.
Something about
Proportional is like this, where
click that
over here you have
you grab the sample images from
you have your set point, you
and,
have your error over here,
and then you have that point.
and over here you have your motor speed.
Oh,
Right? So as your error increases, you're going to increase your motor speed, or whatever it is, and this is multiplied by some constant. That's proportional. What integral is when you do this, what ends up happening, if you look at
Sticking to your program.
position versus time,
Yeah.
what you get with that is you get something that looks like this. This is really bad, right? It's oscillating. So you can get rid of the oscillations with something called the derivative value, which is the D value, which all it does is it'll slow this down so you smoothly end at your set point, which is somewhere over here. What the integral value does is when you do P and you do D, you get something that looks like this.
Yeah.
There's a little space right here, right?
Yeah.
So what the I value does is it says, I'm going to add up, I'm going to add this, and then add that to the motor value. And then I'm going to add this and add it to the motor value. So what ends up happening is this will start to go up and then eventually end at the errors. So the I value gets rid of this error here, which is called the steady state error. It's steady state because your output is, or your position is steady when you do it. It's bringing it even closer. You use it for like the last little bit of the power.
Wait, so then that is this all time to like motion profiling?
Motion profiling is something else. What motion profiling is it lets you say, I want to drive the motor at such and such speed so I get to a position. So if you ever look at the teams that do like splines where they're doing complex turns during autonomous, they do that using motion profiling, which is they say at time 0 I want to drive the motor at this speed, at time 1 I want to drive the motor at this speed, and so on and so forth. They just keep doing that for 15 seconds of autonomous, and then they stop. And then you can also use that for mechanisms too, but it's less helpful because usually this is good enough for that. So yeah, that's what it is. Really look at the videos because this is like my 30-second explanation, like grazing over a lot of details and making assumptions that you shouldn't really make assumptions about.
WPI or something, like on YouTube.
Yeah, here it's right here if you want to like take a picture of it or something.
And then they left. But then they did a bunch of updates for the simulator this year, so they must have got some guys back again. They're making a push into simulation.
So it's right, I think it's this one.
Yeah, the first one's an intro, and that's where he explains it.
Is that Sagansky?
No, that's Dimitri Venerov.
Oh.
Yeah, so that's how PID control works.
Oh, okay, got it.
Thank you.
Yeah, so here.
Thanks so much.
Yeah, sure.
Oh, yes. It's huge. It's huge, and the jobs are, there's tons of jobs, and the salaries are good. It's really nuts.
So imagine you have an arm, just a simple one-link arm, and that arm has to go from horizontal to 90 degrees. How do you do that? How do you provide the motor with the right kinds of commands that lets it move?
Oh, no. So generates a class that implements the grip stuff. And then what you got to do is call some methods in that class from the loop in your program, and then it grips.
So.
Okay. And you can choose the language you want to generate the class in. So you can do Python, C++, Java. So probably if you're like running on a Raspberry Pi or something, Python's really nice because it's very tight, easier to understand programs. Java and C++ are bigger. The programs are a little bigger.
Yeah, I'm looking for it.
Oh, there's a.
Here. So this is the example. It's kind of split up, but what we do here is we copied the grip generated code class into a Eclipse file, and then all the code we needed to run the grip program is here. So you have to like tell it how big your image is, you have to create an image thread, you have to do like 5 or 6 things, and then once you do those 5 or 6 things, it just works running on the robot. Yeah. This is like the meat of the problem. So, and this is copy and paste. You can, I mean, this part is the finding the center of it is not copy and paste. That's where you would write your own code that says, oh, I want the rectangle to be this size and on this part of the screen, and do all the calculations there. When you do this, though, you have to be very careful because you can get weird synchronization errors, which is where you have multiple threads running and one thread like reads a value before another thread writes a value, and then you're getting like 2 sets of values or no values at all if you're using C++.
This runs on your local machine. Right?
This runs on the RobotBuilder.
And then you put your process on the
everything is on
This
the.
example is everything on the RobotBuilder. So
Yeah.
you plug the camera into the RobotBuilder, you take these classes, and you stick them into your robot program on the RobotBuilder, and then it does it there. If you want,
and the output gets sent.
The output is- the output
is sent directly.
It's like right here. Here's the center X of the goal. So if all you're doing is like aiming, right? You know the height of it, then this gets you the X value, and then you use robot. So
Yeah, here's the code. So like from that you get a center X value, and then all you do is
here's the
turns.
The amount of turn is the center X minus the image width divided by 2. So that's how far off left or right it is. It gives you a value that's 0 if you're right on, and positive or negative if you're off. And then you just drive the robot drive thing with a value of 0.6. That's the forward speed, and this is the turn amount. So this is the turn. That's how many degrees off you are, multiplied by a constant to scale it for the motors. So it doesn't turn too fast or too slow.
That's proportional control.
You just mess with this, and that's really the proportional constant, and it makes it so it doesn't go too turn too fast or too slow.
Wait, so once you figure out like how much you're off based on like the middle of, you make like a bounding rectangle.
So
Like, the middle of the rectangle is the middle of like what picture you got. How do you tell the motors?
So for this
How to
example,
connect it?
for this program, for this example, for the thing which this does with vision, which may not be what you want to do this year or last year or the year before that, but for this particular example, all the robot had to do, it got the center X from the vision pipeline, right? That's the center. That's the center of the object, the target that it found, and it tells you the X value of it. So say the thing is 250 pixels wide. It goes, oh, it showed up at pixel 123. It's the center of the target. So you subtract the center X from the camera from the image width divided by 2. So if the image is 250 wide, the image width divided by 2 is like 125, right? So that's the center of it.
Yeah.
And the thing said 123, so you're off by 2 pixels, so you turn accordingly. And
What's the constant to turn by?
so you take the turn, which is either going to be a positive or negative number. That's where 0 is right on.
And then
right?
is that measured in degrees?
It's just measured.
Pixels?
It's just measured in pixels.
Pixels.
Okay. And so it's saying, oh, we're off by some number of pixels, and we'll just multiply it by this value. Now, if you really wanted to be accurate, you do some trig stuff because you can't. It's really there's some sines and cosines in there to compute pixels to angle and stuff. But we just said, who cares? It doesn't matter. If it's further away, we'll turn faster, and if it's closer, we'll turn slower. And the whole goal is to try and turn until the this turn value is 0.
Okay.
And right.
So do you constantly update when you turn?
In this case,
Yeah.
it does. In this case, this is the autonomous periodic method. So periodically, like every 20 milliseconds, in this case, what it would do is get the current image from the camera, do the center X calculation, and then drive the robot towards the goal.
After you guys done, you're more than welcome to come upstairs and grab a few slices
Oh,
of
thank
pizza.
you.
Thank you.
Yeah, well, thank you.
Okay, you get it?
So like this is your image, and like over here is some like target, like X or whatever. And then all we're doing is we're saying, we found the number of pixels between the center and this target, and then we're multiplying by some constant, which will set the motor speed. So to move this target towards the center.
Right, and so if the target is on this side, the value may be negative, and if the target is on this side, the value may be positive, and it turns out with Robot Drive, when you do this thing here, the turn amount, it's a number which 0 means no turn, and negative means turn one way, and positive means turn the other way. So again, this was designed so that you could write this program. All this stuff was designed so you could do this, okay, because it's really simple. So the whole thing was designed with being able to write that program in mind. And
this is like the hardest way to do vision processing. By far the easiest way to do vision processing is to just run grip on your driver station.
That was my next question.
Yeah.
So you pull the image off, you do your process. And
you don't even do that. You just connect grip to the camera. And grip just starts grabbing the camera stream by itself. And it starts giving you values, which you write into network tables, because that's the last step in the pipeline in grip.
Oh, you can it'll write.
It just puts the answers right into network tables. In your robot program, you say, get X, get Y, that kind of,
I understand.
And then you get those values.
You can write
See over here?
that's
He's just publishing, and you can choose what to publish. You can publish the area, the center X, center Y, or there's a whole bunch of other stuff that's down here that you can't see.
Publish or write to network.
Yeah, and then the program in the loop just reads those numbers from network tables instead of from the camera.
Oh, that's an easy way too. We're going to attempt vision this year.
Yes, here, watch this. See, he's holding up that orange thing, and he's just looking for values that only show the orange thing and don't show anything else.
I was never able to get it. I was playing around with those all day, and it was so fun.
Okay, and then you can do contours, and they can find, and then you can filter them because you look for things that are a certain area, minimum area. It's all the little noise goes away, and then pretty soon you just have the little orange thing.
So right now we have like a little bit of artifacts, and the image is really bad because there's.
You see two things that are orange right there. So it's catching his hair, and it's catching the little.
There are two avenues to this. I'm going to try that Pixie too.
The Pixie cam is really nice. And in fact, I've seen teams that use it where it gives you, they threw it on at a competition because one of the modes you can run is it can give you an analog value for either like the X or the Y. Yeah. And so they gave them the analog value, and they read the analog value and they drove the motors at that speed. And that was it. The differential motor thing. And so it said, oh, you're off by, you're off by this much. And that's it. You read the voltage coming out of the Pixie cam. And it tells you how far left or right the target is. So a lot of people, I've seen a bunch of teams that use that. Pretty successful.
Some people like it. Some people said they don't have that well. So I guess it's.
Yeah, I mean the problem with it is it only looks for color blobs. Okay, so in the example that Austin showed before, you could look at the aspect. You can say, oh, these are two rectangles. They're at the same height. They're the same width. The aspect ratio, the difference between the ratio of the height to the width is what those things should be. So it goes, oh yeah, that's the target. But the Pixie cam will just find anything that's that color in the frame and give you that back. And it doesn't tell you, you don't get all that other information necessarily. And so you can't do a lot of that processing. It does give you a lot of that stuff back, but sometimes it's not as much. So the Pixie cam is a great camera to try. And if it works for the game, it's pretty straight. And then do the trick where you use the ring light.
Yes.
Oh, yeah, that's the only way to do it.
The only way to do it.
And then you turn down the camera sensitivity, like way down, so all you see is like really bright.
We've seen some. Yeah. It seems really clear.
Well, that's what those images
Actually, if you have like 2 seconds, we'll steal their camera. And it's really easy to do it because I closed Eclipse.
What are you doing?
I'm going to start a camera server.
Oh.
It's one line of code to start the camera. All it is camera server. Yep. Get instance.start automatic capture. And that's all you need.
And if you go to grid, so he's deploying it now. So the program's getting put onto the robot.
and you don't even need grip. All you have to do is you go to the URL of the camera, and then you can look in outline. You can look in outline viewer for what the URL of the camera is. It'll throw it in there. So if we look, camera publisher, oh, here's the camera. And if we scroll down to find it, oh, here it is. It's at port 1181. So if we type in 1181, we get the camera. And all you have to do is you bring the contrast down, you bring the brightness down, and then suddenly the only thing you can see are the very bright lights. Luckily on an FRC field, if your camera's pointed at the right direction, you don't see any bright lights. All you see is the reflected green. I don't have any retroreflective taper.
Wait, so how did you got the address of the camera?
Yeah, I'm doing this very quickly.
All the cameras get loaded into network tables. All the data about all the cameras and all the values that they're returning and stuff get put into network tables. And so you can go to network table. You can use the outline viewer, which shows you network tables, and you can go find the cameras in there, and then it tells you the URL for the camera string, and which contains the port number. And then you can go to grip, and you can tell it to attach to the camera that's at that port. And then you just write your grip code and run it on the laptop. Is outline viewer new? It's a new version of an old program.
Yeah, so the outline viewer was last updated in 2009, and I rewrote it over the summer.
I usually use the viewer in Eclipse to do it. Is there some viewer? Isn't that? No. In Eclipse itself, under WPI, there's a viewer, and then you can get all the same. You see that?
Yeah, so that is outline viewer.
That is outline viewer? Oh,
yeah,
I'm using it not knowing it.
Yeah, it's this one, right?
Yeah.
Yeah, so that is outline viewer.
Oh, I have an old version that just says viewer or something.
Oh, yeah.
Yeah. Yeah,
oh,
so
I'm using it and I didn't even know
it. It was really old, so we updated it. So now it looks pretty, and it tells you like if you're connected or not, so you know if like you're changing values and nothing's happening, why. And it also lets you like type in your team number instead of typing in the IP address of the RobotRio, or run in server mode, or use a other port. The other cool thing.
This is just like a standalone version of it.
This is a standalone program.
It's shipped with the Eclipse plugins now.
Oh, okay.
The other cool thing that it does, which the old one didn't do, is you can save and load the network table state. So if you don't have your robot with you, or if you're going home for the day, you can save the state in Outline Viewer, and then when you go home, you can keep like rearranging the widgets on the dashboard and playing with it.
As if you were connected to the robot, because it will load up network tables with the values that it had when you went home.
So yeah, that's Outline Viewer. It's my project.
That's your project?
Yeah, that's like I don't know. Yeah, everybody owns a different project, and this is the one that I own. So if you find any problems, it was Peter's, but so if you have any bugs or feature requests, let me know.
Oh, sure. Yeah, I mean, yeah. So look at the beta stuff.
Yeah, we haven't actually even started this year's.
Okay.
So.
Really? So you stopped? Oh.
Yeah, we did. Did we?
Did you ever stop?
That stuff.
Stop doing robot stuff.
She's doing the VEX now.
Yeah, we're
so it never
like
stops.
smaller robots.
You're doing VEX competition?
Yeah, we're just using EDC. So it's
yeah. Not Robot C? They made Robot C free.
We never even heard. Have you heard of Robot C?
Oh, Robot C is something that was developed by this guy, Dick. His last name, I can't remember. But anyway, it lets you write VEX programs in C, and it's pretty nice, and it's free because VEX v5 is coming out soon, so they kind of stopped supporting Robot C and flip into this new thing, which isn't out yet, and so for now you can just use Robot C to program the robots. It doesn't cost anything. You have to like make an account or something, and then just download it, put it on whatever laptops you want. It needs Windows though.
Yeah, real Windows view.